Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the fascinating world of metals, elements that have shaped civilization, built our modern world, and exist all around us in forms both visible and hidden. From the copper in our wires to the iron in our blood, metals are woven into the very fabric of existence. Some are soft enough to cut with a butter knife, while others can withstand temperatures that would vaporize stone. They conduct electricity, reflect light, and hold secrets from the birth of stars themselves. The world of metals is both ordinary and extraordinary, something we touch every day yet rarely pause to truly appreciate. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm wonder of the metallic world to carry you into sleep. Let's begin. Metals make up most of the periodic table. When you look at the periodic table, that colorful chart of elements hanging in chemistry classrooms, you might notice something remarkable. Most of it is metal. Of the 118 known elements, more than 90 are classified as metals. They dominate the table, clustering throughout its center and left side. This isn't coincidence. Metals represent the most common type of element in the universe, formed in the hearts of stars and scattered across space. From lithium, the lightest metal, to the super-heavy synthetic metals created in laboratories, they span an incredible range of properties. Some are shiny and silver, others golden or reddish. Some melt in your hand, while others remain solid at temperatures that would melt rock. Yet they all share certain characteristics: the ability to conduct heat and electricity, a tendency to lose electrons, and often a lustrous appearance. To understand metals is to understand much of the material world itself. Gold has been treasured for over 6,000 years. Gold's allure stretches back to the very beginning of civilization. Archaeological evidence suggests humans have been working with gold for more than 6,000 years. Ancient Egyptians crafted elaborate jewelry and death masks from it. The famous mask of Tutankhamun, gleaming with gold, has captivated observers for millennia. But why gold? Its appeal lies in its unique properties. Unlike iron, gold doesn't rust or tarnish. A gold artifact buried for thousands of years emerges as brilliant as the day it was made. It's soft enough to work without complex tools, yet durable enough to last. Its rich yellow color, unlike any other metal, made it seem touched by the sun itself. Ancient cultures, from the Inca to the Chinese emperors, prized it above all other materials. Gold became synonymous with wealth, power, and the divine. Even today, despite our modern understanding of elements and atoms, gold retains its mystique. Its value remains high, not just for jewelry, but for electronics, where its conductivity and resistance to corrosion make it invaluable. The metal that fascinated ancient goldsmiths still fascinates us today. The name copper comes from the island of Cyprus. Copper has one of the oldest relationships with humanity, and its very name tells a story. The word copper derives from the Latin cuprum, which itself came from the phrase ais cyprium, meaning metal of Cyprus. This Mediterranean island was famous in ancient times for its rich copper mines. The Romans extracted vast quantities of copper from Cyprus, using it for coins, tools, and weapons. But copper's use predates even Rome. The Copper Age, a prehistoric period spanning roughly 5,000 to 3,000 years before Common Era, marks the first time humans worked metal extensively. Early metalworkers discovered that copper could be shaped when heated, then hardened as it cooled. This malleability made it perfect for creating tools superior to stone. When humans learned to mix copper with tin, they created bronze, a harder alloy that would give its name to an entire age of human development. Today, copper remains essential. Its excellent electrical conductivity makes it the metal of choice for wiring in homes, computers, and power grids worldwide. The same metal that built ancient Cyprus now powers modern civilization. Iron is the most abundant metal on Earth. If you could journey to the center of Earth, you would find yourself surrounded by iron. Our planet's core, both outer and inner, consists primarily of iron with some nickel. This makes iron the most abundant metal on Earth by mass, though much of it lies unreachable miles beneath our feet. But even at the surface, iron is remarkably common. It makes up about 5% of Earth's crust, appearing in rocks, soil, and minerals worldwide. Ancient humans discovered iron in meteorites long before they learned to smelt it from ore. These chunks of space metal, fallen from the sky, were considered magical. The Iron Age, beginning around 1200 years before Common Era in the Near East, marked a revolution in human technology. Iron tools and weapons proved superior to bronze, harder and more durable. The metal could be smelted at higher temperatures and was far more abundant than copper or tin. Today, iron, in the form of steel, an alloy with carbon, remains the backbone of modern infrastructure. Bridges, buildings, railways, and vehicles all depend on iron's strength. The most common metal on our planet continues to support the weight of civilization itself. Mercury is the only metal that's liquid at room temperature. Among all the metals, Mercury stands alone in a peculiar way. At ordinary room temperature, Mercury flows like water, a silvery liquid that pools and rolls in mesmerizing droplets. No other metal shares this property. Most metals are solid until heated to high temperatures. Tungsten, for example, doesn't melt until over 3000 degrees. But Mercury remains liquid down to -39 degrees, only solidifying in extremely cold conditions. This unusual property has made Mercury valuable throughout history. Ancient Chinese and Indian civilizations knew of Mercury, believing it held mystical properties. Alchemists attempted to transmute it into gold. In more recent centuries, Mercury found use in thermometers, where its expansion and contraction with temperature made measurements possible. Barometers, switches, and fluorescent lights also employed mercury. However, we now know mercury is highly toxic. Its vapors can damage the nervous system, and its compounds accumulate in the environment. Many uses have been phased out for safety. Yet Mercury remains fascinating, a metal that defies expectations, flowing and shimmering like captured light given liquid form. Aluminum was once more valuable than gold. It's hard to imagine now, when aluminum is used for disposable drink cans and cheap cookware. But this metal was once extraordinarily precious. In the mid-1800s, aluminum was more valuable than gold. The reason was simple. It was incredibly difficult to extract from ore. Aluminum is actually the most abundant metal in Earth's crust, making up about 8% of it, but it never occurs in pure form naturally. It's always locked in compounds, particularly bauxite ore. Early extraction methods were so expensive that aluminum remained a luxury. Napoleon III of France reportedly reserved aluminum cutlery for his most honored guests, while others ate with mere gold utensils. An aluminum cap was placed atop the Washington Monument when completed in 1885, at a time when it was considered a semi-precious metal. Everything changed in 1886, when the Hall-Héroult process was invented, making aluminum cheap to produce through electrolysis. Suddenly, what had been rare became common. Today, aluminum's lightweight, resistance to corrosion, and recyclability make it essential for aircraft, cars, buildings, and packaging. The once precious metal is now everywhere, a testament to how technology can transform scarcity into abundance. Titanium is stronger than steel but weighs half as much. Titanium possesses a remarkable combination of properties that makes it invaluable for modern technology. Pound for pound, it's stronger than steel, yet it weighs roughly half as much. This high strength-to-weight ratio makes it ideal for applications where every ounce matters. Aircraft manufacturers use titanium extensively in jet engines and airframes. The metal can withstand the extreme temperatures and stresses of flight while keeping weight down. Space agencies employ titanium in spacecraft and satellites for the same reasons. Beyond aerospace, titanium has found a home in the human body. It's biocompatible, meaning human tissue accepts it without rejection. Surgeons use titanium for artificial joints, dental implants, and bone plates. The metal integrates with bone, creating lasting repairs. Titanium also resists corrosion remarkably well. It forms a thin oxide layer on its surface that protects it from further degradation. It won't rust like iron or tarnish like silver. This durability means titanium structures can last for generations with minimal maintenance. Despite these impressive qualities, titanium wasn't discovered until 1791, and reliable extraction methods only emerged in the 1900s and 40s. Today, this relative newcomer to metallurgy has become indispensable to modern life. Lead has been used in plumbing for over 2,000 years. The Romans were master engineers, building aqueducts and plumbing systems that supplied water to cities throughout their empire. Their pipes were often made of lead, a metal they called plumbum. This Latin word gives us our modern terms, plumber and plumbing. Lead was ideal for this purpose because it's soft and malleable, easy to shape into pipes and join together. It doesn't corrode readily in water, allowing systems to last for years. Roman plumbers created extensive networks that some historians believe contributed to the empire's success. However, this same lead may have contributed to its decline. Lead is toxic, and chronic exposure causes serious health problems. Lead poisoning affects the nervous system, causing cognitive decline, behavioral issues, and physical ailments. Some historians have speculated that lead in Roman plumbing and in their wine contributed to health problems among the elite. While this theory remains debated, there's no question that lead exposure was widespread. Today, we understand lead's dangers. Many countries have banned lead pipes and lead paint. The process of removing lead plumbing is ongoing in older cities. Yet for centuries, this soft grey metal seemed like a perfect solution, its hidden dangers unknown until modern science revealed them. Silver has natural antibacterial properties. Long before anyone understood the concept of bacteria, humans noticed something unusual about silver. Water stored in silver containers stayed fresh longer. Wounds covered with silver seemed to heal better. The ancient Greeks and Romans used silver vessels for food and drink, and while they attributed this to divine properties, there was a scientific reality beneath the superstition. Silver is naturally antibacterial. When in contact with moisture, it releases silver ions that disrupt bacterial cell walls, effectively killing microorganisms. This property, known as the oligodynamic effect, makes silver useful in medicine and water purification. Modern hospitals use silver-coated bandages for burn victims, where infection is a primary concern. Silver nanoparticles are incorporated into some medical devices to prevent bacterial growth. Water purification systems sometimes use silver to keep water safe during storage. The metal even finds use in some fabrics, creating odor-resistant clothing. Interestingly, colloidal silver, a solution of silver particles suspended in liquid, was used medicinally before antibiotics. While modern medicine has better options, silver's antimicrobial properties remain valuable in specific applications. The ancients were right about silver's protective qualities. Even if they didn't understand why, nature had given them a metal with built-in sterilization properties. Platinum is 30 times rarer than gold. When you think of precious metals, gold likely comes to mind first. But platinum exceeds gold in both rarity and often in value. Platinum is approximately 30 times rarer than gold in Earth's crust. While gold occurs at about 4 parts per billion in crustal rock, platinum appears at just 1/10 of a part per billion. This scarcity is compounded by the difficulty of extraction. Platinum typically occurs mixed with other metals in ores that require complex refining processes. The metal wasn't even recognized as distinct until the 18th century. Spanish conquistadors found it in South America and considered it an inferior form of silver. Platinum means little silver. They actually discarded it. Only later did European scientists realize platinum was a unique element with remarkable properties. Platinum is extremely resistant to corrosion and heat. It maintains its properties at high temperatures where other metals would fail. These characteristics make it essential for catalytic converters in vehicles, which reduce harmful emissions. Platinum also serves in jewelry, laboratory equipment, and as a catalyst in chemical reactions. Its combination of beauty, durability, and rarity keeps platinum among the most valued metals. For every ounce of platinum mined, many tons of ore must be processed. Zinc is essential for human immune function. While we often think of metals as construction materials or precious commodities, some are vital nutrients. Zinc is one of these essential metals. The human body contains approximately 2 to 3 grams of zinc, distributed throughout tissues and fluids. This might seem like a small amount, but zinc is crucial for hundreds of biological processes. It plays a vital role in immune system function. Zinc helps develop and activate T lymphocytes, the white blood cells that fight infections. A zinc deficiency can significantly impair immune response, leaving individuals more susceptible to illness. The metal is also essential for wound healing, DNA synthesis, cell division, and protein creation. During pregnancy and childhood, adequate zinc is crucial for proper growth and development. Interestingly, zinc affects our senses too. It's necessary for proper taste and smell function. People with zinc deficiency sometimes report that food tastes bland or metallic. The mineral is found in foods like meat, shellfish, legumes, seeds, and nuts. Our bodies can't produce zinc, so we must obtain it through diet. The recommended daily intake is modest, around 11 milligrams for adults. Yet this trace amount of metal makes the difference between health and vulnerability. Zinc reminds us that we are, quite literally, made of the same elements as the stars and Earth. Tungsten has the highest melting point of any metal. Imagine a metal so resistant to heat that it can withstand temperatures exceeding 3,400 degrees. That's tungsten, the champion of high-temperature endurance. Its melting point is the highest of all metals, surpassing even the fierce heat inside many industrial furnaces. This extraordinary property comes from tungsten's atomic structure. Its atoms bond together with exceptional strength, requiring tremendous energy to break apart. The name tungsten comes from Swedish words meaning heavy stone, and heavy it is, nearly as dense as gold. Tungsten's heat resistance makes it indispensable in applications involving extreme temperatures. It's the metal inside traditional incandescent light bulb filaments. When electricity flows through a thin tungsten wire, it heats to over 2,000 degrees, glowing white hot without melting. The bulbs that lit homes for over a century relied on tungsten's ability to glow brightly without failing. Today, Tungsten finds use in welding electrodes, rocket engine nozzles, and high-speed cutting tools. It's alloyed with other metals to create materials that maintain strength and hardness, even in blazing heat. In its pure form, tungsten is brittle, but when properly alloyed, it becomes incredibly useful. This is a metal that laughs at temperatures that would reduce most materials to molten pools. Bronze was the first alloy humans created intentionally. Human mastery of metals took a monumental leap forward when ancient metal workers discovered that mixing copper with tin created something superior to either metal alone. This was bronze, and its creation marks humanity's first deliberate alloy. The Bronze Age, lasting roughly from 3,300 to 1,200 years before Common Era in the Near East, transformed society. Bronze is harder than copper, holds an edge better, and casts more easily into molds. These properties made it ideal for tools, weapons, and decorative objects. Civilizations that mastered bronze production gained significant advantages. They could create more effective farming implements, increasing food production. Their weapons and armor gave them military superiority. Bronze sculptures and vessels demonstrated wealth and artistic achievement. The process of creating bronze required sophisticated knowledge. Metalworkers had to source both copper and tin, often from different regions. They needed to understand the right proportions, typically around 90% copper to 10% tin, though ratios varied for different uses. They had to control furnace temperatures and master casting techniques. This knowledge spread along trade routes, connecting distant cultures through the pursuit of better materials. When you hold a bronze object today, you're touching a technology over 5,000 years old, one of humanity's first great material innovations. Stainless steel contains chromium to resist rust. We take stainless steel for granted today, seeing it in cutlery, appliances, medical instruments, and architecture. But this corrosion-resistant material only emerged in the early 20th century. Regular steel, an alloy of iron and carbon, is strong but vulnerable to rust. When exposed to moisture and oxygen, iron oxidizes, forming that familiar reddish-brown decay that weakens metal. For centuries, this was simply accepted. Metal rusted, and you dealt with it through paint, oil, or replacement. The breakthrough came when metallurgists discovered that adding chromium to steel creates a protective barrier. When stainless steel contains at least 10 to 12% chromium, something remarkable happens. The chromium reacts with oxygen to form a thin, invisible layer of chromium oxide on the metal's surface. This layer is incredibly stable and adheres tightly to the underlying steel. It prevents further oxygen from reaching the iron beneath, stopping rust before it starts. If the surface is scratched, the chromium oxide layer reforms automatically, creating self-healing protection. This discovery revolutionized industries. Suddenly, metal could be used in damp, corrosive environments without constant maintenance. Surgical instruments could be sterilized repeatedly without degrading. Kitchen sinks and appliances could withstand water exposure indefinitely. Stainless steel bridges and buildings could weather storms for decades. By understanding how metals interact at the atomic level, we transformed a weakness into strength. The Statue of Liberty is coated in copper that has turned green. When the Statue of Liberty was unveiled in 1886, it gleamed with the bright, reddish-brown color of fresh copper. The statue's skin consists of copper sheets, about the thickness of 2 pennies, shaped and hammered to form Liberty's iconic figure. But if you've seen the statue, you know it's not copper-colored anymore. It's green, a soft blue-green patina that has become part of its identity. This transformation happened gradually over decades as the copper reacted with moisture, oxygen, and pollutants in the air. The process created a layer of copper carbonate and copper sulfate on the surface. This patina, far from being damaged, actually protects the copper beneath from further corrosion. It's a natural preservative that has helped the statue endure for over a century. Interestingly, authorities have debated whether to remove the patina and restore the original copper color. In the 1980s, during a major restoration, engineers discovered some areas where the patina had been compromised. They repaired these sections, but deliberately allowed the patina to remain and reform. The green color, they decided, had become too iconic to remove. Today, that green statue, the result of natural chemical processes, stands as a symbol recognized worldwide. The copper's transformation reminds us that metals are not static. They interact with their environment, creating beauty through change. Brass is an alloy of copper and zinc, known for its golden appearance. Walk into a building with polished brass fixtures, and you're immediately struck by their warm, golden glow. Brass has been prized for centuries, precisely because it resembles gold while being far more affordable and practical. This alloy consists primarily of copper mixed with zinc, typically in proportions ranging from 60 to 40% copper to 40 to 60% zinc. The exact ratio determines the alloy's properties. More zinc creates a harder, stronger brass. More copper gives a redder color and greater corrosion resistance. Brass has been used for at least 2,500 years, though ancient metalworkers didn't fully understand what they were creating. They would heat copper with calamine ore, a zinc-containing mineral, and produce brass through a process they couldn't quite explain. The zinc vaporized and alloyed with the copper, creating the golden metal. Today, brass finds use in musical instruments, where its acoustic properties produce beautiful tones. Trumpets, trombones, saxophones, and French horns are typically brass. The metal is also used for ammunition casings, plumbing fittings, decorative hardware, and marine applications. Brass resists corrosion better than iron and machines more easily than many metals. It's antimicrobial, like copper and silver, making it suitable for door handles and fixtures in public spaces. This versatile alloy bridges the practical and the beautiful, bringing a touch of gold into everyday objects. Sodium is a metal so reactive it bursts into flame when touching water. Most people know sodium as part of table salt, sodium chloride, a white crystalline substance essential to life. But pure sodium metal is something entirely different, dangerous, reactive, and fascinating. In its elemental form, sodium is a soft, silvery white metal that can be cut with a knife. It's so reactive that it must be stored under oil to prevent contact with moisture in the air. If you drop a chunk of sodium into water, the result is immediate and dramatic. The metal races across the water's surface, hissing and fizzing as it reacts violently. It releases hydrogen gas and generates so much heat that the hydrogen can ignite, producing flames that dance across the water's surface. If you use a large enough piece, the reaction can be explosive. This extreme reactivity explains why sodium never occurs in nature as a pure metal. It's always found in compounds, bound to other elements. Yet sodium is essential for life. Our nervous systems use sodium ions to transmit electrical signals between cells. Every thought you have, every movement you make, depends on sodium. The concentration of sodium in our blood is carefully regulated. Too much or too little can be dangerous. It's remarkable that an element so violently reactive in its pure form is so crucial to our existence when properly bound in compounds. Magnesium burns with an intensely bright white light. If you've ever seen an old-fashioned camera flash bulb or emergency flare, you've witnessed magnesium's spectacular property. When ignited, magnesium burns with an incredibly bright white light. The intensity is so great that looking directly at burning magnesium can damage your eyes. This property made magnesium invaluable for photography in the days before electronic flashes. Photographers would ignite magnesium powder or ribbon to create the burst of light needed to expose film. The distinctive white smoke and acrid smell became synonymous with press photography. Magnesium's brightness comes from the tremendous energy released when it combines with oxygen. The reaction is exothermic, producing temperatures around 3000 degrees. The metal burns so hot that it can continue burning even underwater, pulling oxygen from the water molecules themselves. This makes magnesium fires notoriously difficult to extinguish. Throwing water on burning magnesium only feeds the flames. Despite this reactivity, or perhaps because of it, magnesium is essential for life. It's the central atom in chlorophyll, the molecule that makes plants green and enables photosynthesis. Without magnesium, plants couldn't convert sunlight into energy, and the food chain would collapse. In human bodies, magnesium is the fourth most abundant mineral, crucial for over 300 biochemical reactions. It helps muscles contract and relax, including the heart. The same element that burns with blinding light quietly enables life itself. Nickel gets its name from a mischievous goblin. The story of nickel's name is one of frustration and folklore. German miners in the 16th century searching for copper encountered a reddish ore that looked promising. But when smelted, it yielded not copper, but a troublesome, unworkable metal. Frustrated miners blamed supernatural creatures. They called the ore Kupfernickel, meaning copper demon or goblin. Nickel was the name of mischievous goblin-like spirits from German mythology, tricksters who led miners astray. The ore, they believed, had been cursed by these nickels. In 1751, Swedish chemist Axel Fredrik Cronstedt isolated the metal and gave it the name nickel, honoring the miners' folklore. For years, nickel was considered a nuisance. It wasn't until the 19th century that its value became clear. Nickel is corrosion resistant, making it excellent for plating other metals. Mixed with iron and chromium, it creates stainless steel. Combined with copper, it forms cupronickel, the alloy used in many coins worldwide. Today, nickel is essential for batteries, particularly the rechargeable batteries in electric vehicles. It's also used in superalloys for jet engines and power generation turbines. The troublesome goblin metal turned out to be treasure after all. Sometimes what seems like a curse is simply something waiting to be understood. The miners' demons became our valuable resource. Cobalt creates the most vibrant blue pigments. For thousands of years, achieving a vivid, stable blue pigment was the holy grail of artists and craftsmen. Many blues faded over time or were difficult to produce. Then came cobalt blue, a pigment so striking and permanent that it revolutionized art. Cobalt compounds, particularly cobalt aluminate, produce an intense, pure blue, unlike any other. The color is so distinctive that cobalt blue became a standard, the ideal against which other blues are measured. Ancient Egyptians and Mesopotamians used cobalt-containing minerals to create blue glass and ceramics, though they didn't isolate the element itself. Chinese porcelain makers used cobalt to create their famous blue and white designs. The pigment gained particular fame in European painting during the 19th century. Artists like J.M.W. Turner embraced cobalt blue for its brilliance and reliability. Unlike some pigments that reacted with others or faded in light, cobalt blue remained stable and true. Beyond art, cobalt's vivid color found use in glassmaking, creating everything from bottles to stained glass windows. The blue glass used in old apothecary bottles often contained cobalt. Today, cobalt remains important for pigments, but it has other critical uses. It's essential in rechargeable batteries, particularly lithium-ion batteries. It's used in superalloys for high-temperature applications. Yet for many, cobalt will always be associated first with that distinctive, unforgettable blue. Lithium is the lightest metal in existence. Among all the metals, lithium holds a unique distinction. It is the lightest, with a density less than half that of water. If you dropped lithium into a container of water, it would float, bobbing on the surface like wood. Of course, doing this would be dramatic, as lithium reacts vigorously with water, producing hydrogen gas and heat. But setting aside its reactivity, lithium's low density is remarkable. This lightness comes from lithium's atomic structure. It has only 3 protons in its nucleus, making it the lightest metal on the periodic table. Despite being a metal, pure lithium is soft enough to cut with a knife and has a silvery white appearance. Lithium's combination of light, weight, and electrochemical properties makes it ideal for batteries. Lithium-ion batteries power smartphones, laptops, electric vehicles, and countless other devices. They store more energy per unit of weight than most other rechargeable battery types. This advantage becomes crucial in applications where weight matters, like in vehicles or portable electronics. Beyond batteries, lithium has medical applications. Lithium compounds are used to treat bipolar disorder, helping to stabilize mood swings. The mechanism isn't fully understood, but lithium ions appear to affect neurotransmitter systems in the brain. A metal, lighter than water, floating between reactivity and utility, powering both our devices and, in some cases, helping to balance human minds. Uranium glows green under ultraviolet light. Uranium, perhaps most famous for its role in nuclear power and weapons, has a curious property that seems almost magical. When exposed to ultraviolet light, uranium compounds fluoresce, glowing with an eerie, vibrant green color. This glow has nothing to do with radioactivity. It's a property of how uranium atoms absorb and re-emit light at certain wavelengths. In the 19th and early 20th centuries, before uranium's radioactive properties were fully understood, it was used in glassmaking. Uranium glass, also called Vaseline glass, because of its yellowish-green tint, was popular for decorative items. Under normal light, these pieces appear pale yellow or greenish, but shine a black light on them, and they burst into brilliant green fluorescence. Collectors today seek out these glowing antiques. The radioactivity in uranium glass is generally considered low enough to be safe for display, though not recommended for food use. Uranium was also used in ceramic glazes, particularly for orange and red colors. These glazes, called Fiestaware Red in one famous application, were produced from the 1920s through the 1940s. The radioactivity is minimal, but measurable. Today, uranium's primary significance lies in nuclear energy and medicine. Uranium-235 can sustain nuclear fission, releasing enormous amounts of energy. 1 kilogram of uranium can produce as much energy as millions of kilograms of coal. Yet that ghostly green glow remains one of uranium's most visually striking features. Gallium melts in your hand. Imagine a metal that looks solid and substantial, but when you hold it in your palm, it begins to melt, turning into a silvery liquid pool. This is gallium, a metal with a melting point of just under 30 degrees, slightly below normal human body temperature. At room temperature, gallium is solid, with a bluish-silver appearance. But the warmth of your hand is enough to transform it. This unusual property makes gallium a favorite for science demonstrations. Watching solid metal melt from body heat alone never fails to intrigue. It challenges our expectations about what metal should be. Gallium is also notable for another quirky behavior. Like water, it expands when it solidifies. This is rare among materials. Most substances contract when freezing. Gallium's expansion means you shouldn't store it in rigid containers, as it can crack them when solidifying. Despite its low melting point, gallium has practical applications. It's used in electronics, particularly in gallium arsenide semiconductors, which are faster than silicon in certain applications. Gallium nitride is used in blue LEDs and high-power electronics. Gallium-based alloys serve as non-toxic alternatives to mercury in some applications. Some gallium alloys remain liquid at room temperature, while being far safer to handle than mercury. Gallium also has medical uses. Gallium scans in nuclear medicine help detect inflammation and tumors. This quirky metal that melts in your hand turns out to be surprisingly useful. Chromium is named after the Greek word for color. Open a box of crayons, and you'll find colors spanning the spectrum. The word chromium shares its root with these vivid hues. The name comes from the Greek word chroma, meaning color. Chromium earns this name because its compounds produce a stunning array of colors. Chromium salts can be yellow, orange, red, green, or violet, depending on their oxidation state and chemical structure. This property made chromium valuable for pigments and dyes long before its other uses were discovered. Chromium yellow, a lead chromate pigment, produces a bright, warm yellow. It was favored by painters in the 19th century, appearing in works by Van Gogh and others. Chrome green creates a rich, stable green for paints and inks. Chrome red offers a vibrant crimson. These chromium-based pigments are generally more durable and fade-resistant than organic dyes. Beyond pigments, chromium's most important use is in metallurgy. Adding chromium to steel creates stainless steel, as mentioned earlier. But chromium is also used in chrome plating, that shiny, mirror-like finish on car bumpers, faucets, and tools. The process deposits a thin layer of chromium onto a surface, providing corrosion resistance and a lustrous appearance. Pure chromium is a hard, brittle metal with a distinctive steel gray color. It's this versatility, transforming from shiny protective coating to source of rainbow hues, that makes chromium live up to its colorful name. Tin has been alloyed with copper for over 5,000 years. Tin's partnership with copper in forming bronze makes it one of the most historically significant metals. But tin has other fascinating properties. At temperatures below 13 degrees, regular tin undergoes a transformation known as tin pest. The metal's crystalline structure changes from its normal form, called beta tin, to a more brittle form, called alpha tin. This transformation causes the metal to crumble into a gray powder. The process is slow and requires sustained cold, so it's rarely encountered in everyday life. But it can destroy tin objects exposed to prolonged freezing conditions. There are stories, possibly apocryphal, of tin buttons on soldiers' uniforms disintegrating during Napoleon's retreat from Russia in the brutal winter of 1812. Whether true or not, the phenomenon is real. Tin pest serves as a reminder that metals can have different forms depending on conditions. Tin is also notable for its use in tin cans, though modern cans are actually steel coated with a thin layer of tin. The tin protects the steel from corrosion and prevents the food from acquiring a metallic taste. Tin plating has been used for centuries to protect other metals. Pewter, a traditional metal for plates and tankards, is primarily tin with small amounts of other metals. Tin solder, an alloy of tin and lead, was once ubiquitous for joining electronic components, though lead-free alternatives are now preferred. Tin's role may be supporting other materials, but it's an essential supporting role. Osmium is the densest naturally occurring element. Density is a measure of how much mass is packed into a given volume. Most metals are dense compared to non-metals. Gold feels heavy for its size. Lead is famously dense, but osmium surpasses them all. Osmium, a hard, brittle, bluish-white metal, is the densest naturally occurring element. Its density is approximately twice that of lead and slightly higher than iridium, its closest competitor. A liter of osmium weighs about 22.6 kilograms, over 49 pounds. Holding a chunk of osmium, you'd be surprised by its weight. It feels denser than seems possible. Osmium belongs to the platinum group metals and is extremely rare. It's also quite difficult to work with. In its pure form, osmium oxidizes readily when heated, producing osmium tetroxide, a toxic and pungent compound. This volatility limits osmium's applications. However, when alloyed with other platinum group metals, particularly iridium, osmium becomes more stable and useful. Osmium-iridium alloys are among the hardest materials known. They're used for applications requiring extreme durability, like the tips of fountain pen nibs or electrical contacts. Osmium has also been used in microscopy. Osmium tetroxide, despite its toxicity, serves as a staining agent for biological samples in electron microscopy, helping reveal cellular structures. This heaviest of elements, dense enough to feel wrong in your hand, finds its niche in the finest details, from the point of a pen to the view inside a cell. Palladium can absorb up to 900 times its volume of hydrogen. Imagine a metal that acts like a sponge for hydrogen gas. That's palladium, a silvery white metal from the platinum group. When exposed to hydrogen, palladium absorbs the gas into its crystal structure. The hydrogen atoms slip between the palladium atoms, storing inside the metal. Remarkably, palladium can absorb up to 900 times its own volume of hydrogen. The metal swells slightly as it absorbs, then contracts when the hydrogen is released. This property makes palladium valuable for hydrogen purification and storage. Palladium membranes can filter hydrogen from mixed gases, allowing only hydrogen to pass through. This is useful in producing ultra-pure hydrogen for industrial processes. Palladium's ability to absorb hydrogen also makes it a key component in catalytic converters. These devices, found in vehicle exhaust systems, use palladium along with platinum and rhodium to catalyze chemical reactions that convert harmful pollutants into less harmful substances. Carbon monoxide becomes carbon dioxide. Nitrogen oxides become nitrogen and oxygen, and unburned hydrocarbons become carbon dioxide and water. Beyond environmental applications, palladium is used in electronics, dentistry, and jewelry. White gold often contains palladium. The metal's ability to act as a hydrogen sponge has even sparked research into hydrogen-powered vehicles. Imagine a fuel tank that's a block of palladium-based alloy, safely storing hydrogen and releasing it as needed. This relatively obscure metal plays a crucial role in making our air cleaner and our future more sustainable. Tantalum is used in medical implants and electronics. Tantalum is a metal that exemplifies versatility. It's hard, dense, and has an extremely high melting point, over 3,000 degrees. But what makes tantalum particularly special is its biocompatibility and resistance to corrosion. Tantalum is almost entirely immune to corrosion by acids, even the most aggressive ones. Only hydrofluoric acid and certain hot alkaline solutions attack it. This near-total resistance to chemical attack makes tantalum ideal for applications in harsh environments. In medicine, tantalum's biocompatibility means the human body doesn't reject it. Surgeons use tantalum for bone repair and replacement. Tantalum implants and meshes help repair skull and facial bones. The metal integrates well with bone tissue, allowing natural healing. In electronics, Tantalum capacitors are prized for their reliability and stability. These small components store electrical charge in devices ranging from smartphones to spacecraft. Tantalum capacitors are particularly good at maintaining their properties over time and across temperature ranges. The metal is also used in high-end audio equipment and computers. Tantalum's rarity and difficulty of extraction make it relatively expensive. It's obtained primarily as a byproduct of tin mining and from a mineral called coltan. Ethical concerns have sometimes surrounded tantalum mining, as coltan deposits in conflict regions have been linked to financing armed groups. Responsible sourcing has become increasingly important. This tough, resistant metal connects our bodies and our technology, enabling both healing and communication. Bismuth forms beautiful rainbow-colored crystals. Most people don't think of metals as colorful, but bismuth breaks that expectation spectacularly. When bismuth solidifies from its molten state, it can form hopper crystals, intricate geometric structures with a stepped, spiraling appearance. These crystals look almost artificial, like something from a science fiction movie. But what truly sets bismuth apart is the rainbow of colors that dance across its surface. Pinks, purples, blues, yellows, and greens shimmer and shift as you move the crystal. These colors aren't pigments. They result from a thin oxide layer that forms on the bismuth's surface. The layer's thickness varies across the crystal, and different thicknesses interfere with light waves differently, producing an effect called thin film interference. It's the same phenomenon that creates colors in soap bubbles or oil slicks. Bismuth itself is a brittle, crystalline metal with a pinkish-white color when freshly broken. It has one of the lowest thermal conductivities of all metals, meaning it doesn't transfer heat well. Bismuth is also slightly radioactive, though its half-life is so long, over 1 billion times the age of the universe, that this is effectively meaningless. Bismuth compounds have medical uses. Bismuth subsalicylate is the active ingredient in Pepto-Bismol, treating digestive issues. Bismuth is also used in cosmetics and some solders. But for many, bismuth's appeal is aesthetic. Growing bismuth crystals has become a hobby, producing natural art pieces that blur the line between chemistry and beauty. Vanadium is named after a Norse goddess of beauty. The story of vanadium's name is steeped in mythology and chemistry. In the 1800s and 20s, Swedish chemist Nils Gabriel Säfström discovered a new element. Struck by the beautiful array of colors its compounds displayed, reds, oranges, yellows, blues, and greens, he named it vanadium after Vanadis, another name for Freya, the Norse goddess of beauty, love, and fertility. Like chromium, vanadium's compounds are notably colorful, making the mythological reference fitting. But vanadium's importance extends far beyond aesthetics. This steel-gray metal is primarily used as an alloying element in steel. Adding just a small percentage of vanadium to steel significantly increases its strength and toughness while reducing its weight. Vanadium steel is used in tools, particularly high-speed cutting tools that need to maintain their edge at high temperatures. The metal's ability to strengthen steel made it valuable for automotive and aerospace applications. Early Ford Model T cars used vanadium steel in their chassis, contributing to the vehicles being both strong and relatively light. Vanadium is also used in titanium alloys and in creating superconductive magnets. Interestingly, some living organisms use vanadium. Certain sea creatures, like tunicates, accumulate vanadium in their blood cells, though the purpose isn't entirely clear. Vanadium compounds are also being researched for potential diabetes treatments. From Norse mythology to modern medicine, from colorful compounds to strong alloys, Vanadium spans a remarkable range. Indium is soft enough to leave marks on paper. Most metals are hard. We expect them to be solid, unyielding substances. Indium challenges this expectation. This silvery white metal is so soft that you can scratch it with a fingernail. If you rub indium against paper, it leaves a mark, not unlike a pencil. When bent, indium emits a distinctive high-pitched cry, a sound caused by the crystals in the metal deforming. This cry is sometimes called a tin cry, as tin makes a similar sound, though indium's is higher pitched. Despite its softness, indium has become technologically important. Its primary use is in indium tin oxide, or ITO, a transparent conducting material. ITO coats the screens of smartphones, tablets, computer monitors, and televisions. The coating conducts electricity while remaining transparent, allowing touchscreens to function. Without indium, the touchscreen revolution might not have been possible. Indium is also used in solders, particularly low melting point solders for delicate electronic work. It's employed in some semiconductors and in creating mirrors for high-quality optical systems. Indium is relatively rare, with no primary indium mines. Instead, it's obtained as a byproduct of zinc refining. The growing demand for touchscreens and flat panel displays has made indium an increasingly valuable metal. Something you've probably never heard of is in nearly every modern screen you touch. The soft metal that cries when bent has become essential to how we interact with technology. Rhenium is one of the rarest metals in Earth's crust. Rarity is relative in the world of metals. Gold is rare, occurring at about 4 parts per billion in Earth's crust. But rhenium is rarer still. This silvery white metal occurs at concentrations of only about 1 part per billion, making it one of the rarest stable elements. Rhenium wasn't discovered until 1925, making it one of the last naturally occurring elements to be identified. The name comes from Rhenus, the Latin name for the Rhine River, honoring the river that flows through Germany where the discoverers worked. Rhenium has an extraordinarily high melting point, exceeded among pure elements only by tungsten and carbon. It's also extremely dense and resistant to wear and corrosion. These properties make rhenium valuable for high-temperature applications. Its primary use is in superalloys for jet engine turbine blades. Adding rhenium to nickel-based superalloys increases their temperature resistance, allowing engines to run hotter and more efficiently. This improves fuel economy and performance. A single modern jet engine contains several kilograms of rhenium. The metal is also used in catalysts for petroleum refining and in thermocouples for measuring high temperatures. Rhenium's scarcity and difficult extraction make it expensive, often more costly than gold. Yet for aerospace applications where performance is critical, the cost is justified. This ultra-rare metal, unknown to science a century ago, now flies through the skies in nearly every commercial jet, testament to how even the rarest materials find their essential roles. Radium glows in the dark due to radioactivity. In the early 20th century, a new element captured the public imagination like few others. Radium, discovered by Marie and Pierre Curie in 1898, glowed with an eerie, ghostly light. This wasn't fluorescence requiring external light. Radium glows continuously on its own, a phenomenon caused by its intense radioactivity. The radiation excites molecules in the air around it, causing them to emit light. This self-luminescence seemed almost magical. Radium was incorporated into glow-in-the-dark paint used on watch dials, instrument panels, and novelty items. Workers, mostly young women, painted these dials by hand, often licking their brushes to make fine points. These radium girls, as they became known, suffered terrible health consequences. Radium is chemically similar to calcium, so when ingested or absorbed, it concentrates in bones. There, it emits radiation that destroys tissue, leading to bone fractures, anemia, and cancers. Many radium dial painters developed devastating illnesses. Their suffering eventually led to improved labor laws and better understanding of radiation safety. Today, radium's glow has lost its luster. We understand it as a dangerous radioactive element with a half-life of about 1600 years for its most stable isotope. It has virtually no commercial uses anymore, too hazardous to justify. But radium's story remains important. It reminds us that beauty can conceal danger, and that understanding the true nature of materials protects us from repeating past mistakes. The glowing wonder became a cautionary tale about radiation's hidden perils. Cesium is one of the most reactive metals. The alkali metals, the first column of the periodic table, are all highly reactive. They react vigorously with water and must be stored carefully. As you move down this column, reactivity increases. Cesium, near the bottom, is one of the most reactive metals known. This soft, silvery gold metal melts at just over 28 degrees, close to room temperature. Like sodium, it must be stored in an inert atmosphere or under oil to prevent reaction with air. But cesium's reaction with water makes sodium look tame. Drop cesium into water and it explodes almost immediately. The reaction is so violent and rapid that the metal often doesn't even have time to melt. It detonates, producing a powerful explosion that can shatter containers. This extreme reactivity means cesium is purely a laboratory curiosity in its pure form. It has no practical uses as elemental metal. However, cesium compounds and ions have important applications. Cesium atomic clocks are among the most accurate timekeeping devices ever created. They define the second in the International System of Units. 1 second is defined as the duration of 9,192,631,770 oscillations of radiation, corresponding to the transition between two energy levels of cesium-133. These clocks are so precise they would lose less than 1 second over millions of years. GPS satellites carry cesium clocks, and their accuracy is essential for navigation. The most reactive of metals, too dangerous to handle casually, nonetheless helps us measure time itself with unprecedented precision. Yttrium is part of rare earth elements used in LED lights. Yttrium, despite its name suggesting rarity, is actually more abundant than lead in Earth's crust. The confusion comes from its classification among the rare earth elements, a group of metals that are not particularly rare, but were difficult to separate and extract when first discovered. Yttrium is a silvery metallic element that has become crucial for modern lighting and display technologies. One of yttrium's most important applications is in phosphors, materials that emit light when excited by energy. Yttrium aluminum garnet, or YAG, doped with other rare earth elements like cerium, creates the phosphors used in white LED lights. These LEDs have revolutionized lighting, providing energy-efficient illumination that has replaced incandescent bulbs worldwide. The white light from these LEDs starts as blue light from a gallium nitride LED chip. This blue light then excites the YAG phosphor coating, which emits yellow light. The combination of blue and yellow appears white to our eyes. By adjusting the phosphor composition, manufacturers can create different color temperatures, from warm white to cool white. Yttrium is also used in lasers, particularly yttrium aluminum garnet lasers used in medicine and industry. It's a component in some superconductors and in materials for jet engine coatings. The element is named after Ytterby, a village in Sweden, where many rare earth elements were first discovered in minerals from a nearby quarry. This one small location gave its name to Yttrium, Ytterbium, Terbium, and Erbium. From a Swedish village to LED lights illuminating the world, Yttrium's journey spans centuries and continents. Beryllium is light, strong, and unfortunately toxic. Beryllium sits at the top of the alkaline earth metals, the second column of the periodic table. It's a steel-gray metal that is remarkably light, with a density similar to magnesium, but significantly less than aluminum. What makes beryllium special is its combination of low density, high stiffness, and good thermal properties. Beryllium is stiffer than steel but weighs only about a third as much. This makes it ideal for applications where weight savings and rigidity are both critical. Beryllium is used in aerospace and defense applications, in X-ray equipment, where its transparency to X-rays is valuable, in high-end audio speakers, where its stiffness improves sound quality, and in various precision instruments. Beryllium-copper alloys combine strength with electrical conductivity and are used in electronic connectors and springs. The James Webb Space Telescope's mirrors are made of beryllium, chosen for its light weight and ability to maintain shape in the extreme cold of space. However, beryllium has a dark side. Beryllium dust and vapors are highly toxic. Inhaling them can cause berylliosis, a chronic lung disease similar to sarcoidosis. The lungs become inflamed and scarred, leading to difficulty breathing and other serious health issues. There is no cure for berylliosis. Because of this toxicity, working with beryllium requires strict safety protocols. Machining, grinding, or heating beryllium must be done with proper ventilation and protective equipment. The metal that helps us see the earliest galaxies and hear music with clarity must be handled with respect and care. Its benefits balanced against its hazards. Thorium could power nuclear reactors of the future. When people think of nuclear power, uranium typically comes to mind. But another metal, thorium, has been proposed as a potentially safer and more abundant alternative. Thorium is a slightly radioactive metal, more abundant in Earth's crust than uranium. It cannot sustain a nuclear chain reaction on its own, but when bombarded with neutrons, thorium-232 can convert to uranium-233, which is fissile and can fuel nuclear reactions. This process could form the basis of thorium-based nuclear reactors. Advocates of thorium reactors point to several potential advantages. Thorium is more abundant than uranium, widely distributed across the globe. Thorium reactors could be designed to be inherently safer, with the reaction naturally slowing if something goes wrong rather than accelerating. The waste from thorium reactors would remain hazardous for hundreds of years rather than thousands. Thorium reactors are also more difficult to use for producing weapons-grade material. Despite these potential benefits, thorium reactor technology remains largely experimental. Only a few countries have built or are developing thorium reactors. The existing nuclear infrastructure is built around uranium, and changing would require significant investment and development. Questions remain about long-term viability, waste handling, and economic competitiveness. Thorium was named after Thor, the Norse god of thunder, by its discoverer in 1829. Whether this powerful element will bring a new age of nuclear energy or remain a promising but unrealized possibility, only time will tell. The metal named for thunder waits to see if it will spark a revolution. Cadmium creates brilliant yellow and red pigments. Cadmium is a soft, bluish-white metal, primarily known today for its toxicity and its use in rechargeable batteries. But for over a century, cadmium has played a crucial role in art through its pigments. Cadmium yellow and cadmium red are among the most brilliant, pure and light-fast pigments available. Cadmium yellow ranges from pale, lemony yellows to deep, orangish yellows. Cadmium red produces vivid, warm reds and oranges. These colors are so vibrant and stable that they became favorites of artists. Vincent van Gogh used cadmium yellow in his sunflower paintings. Henri Matisse relied on cadmium reds in his Fauvist works. Claude Monet incorporated cadmium colors in his Water Lily series. The pigments don't fade in sunlight, don't react with other pigments, and maintain their brilliance over time. However, cadmium's toxicity has raised concerns. Cadmium and its compounds are classified as carcinogens. Exposure can damage kidneys and bones. While the cadmium in dried paint is generally stable and low risk, some artists and art supply manufacturers have moved toward cadmium-free alternatives. Modern formulations can approximate cadmium's hues using other pigments, though purists argue nothing quite matches cadmium's intensity. Beyond art, cadmium was used in yellow road paint, though this practice has declined. Cadmium is used in nickel-cadmium rechargeable batteries, though these too are being phased out in favor of less toxic alternatives. Cadmium's legacy in art remains strong. Museums worldwide preserve paintings colored with cadmium pigments, their brightness enduring as testament to the metal's unique properties. The toxic metal that created beauty continues to shine from canvas walls. Antimony has been used in cosmetics for thousands of years. Antimony is a metalloid, an element with properties between metals and non-metals. It has a silvery, lustrous appearance and is brittle, fracturing rather than bending. Antimony's history with humanity is long and complex. Ancient Egyptians used antimony sulfide, a naturally occurring mineral called stibnite, as a cosmetic. Ground into powder and mixed with fat, it created kohl, the distinctive black eye makeup seen in Egyptian art. Cleopatra and countless others darkened their eyelids with antimony-based kohl. The practice spread throughout the ancient world and continues in some cultures today. In medieval times, antimony compounds were used in medicines, though often with disastrous results due to toxicity. Alchemists were fascinated by antimony, believing it had mystical properties. Today, antimony's primary use is in flame retardants. Antimony trioxide is added to plastics, textiles, and other materials to reduce flammability. It's also used in lead-acid batteries, in semiconductors, and in specialized alloys. Antimony has unusual expansion properties. Like water, it expands when solidifying. This made it useful in type metal for printing, as the expanding antimony ensured sharp, clear impressions. The metal is also used in pewter, lead, crystal glass, and ammunition. Antimony is toxic in significant amounts, which has led to its cosmetic use being controversial in modern times. Some coal products still contain antimony, and health authorities have warned against their use, especially for children. Yet this ancient cosmetic remains popular in some regions, carrying forward a practice thousands of years old. From Cleopatra's eyes to modern fire safety, antimony's journey is uniquely human. Hafnium is used in nuclear reactor control rods. Hafnium is a shiny, silvery metal that most people have never heard of, yet it plays a crucial role in nuclear technology. This metal has an extraordinary property. It absorbs neutrons extremely effectively. In a nuclear reactor, controlling the rate of fission reactions is essential for safety and power regulation. Control rods made of neutron-absorbing materials are inserted into or withdrawn from the reactor core to control the reaction. Hafnium is one of the best materials for this purpose. When hafnium control rods are inserted deeper into a reactor core, they absorb more neutrons, slowing or stopping the fission chain reaction. When withdrawn, more neutrons are available to sustain the reaction, increasing power output. Hafnium's neutron absorption properties, combined with its resistance to corrosion and high melting point, make it ideal for this application. The metal is also used in superalloys, for jet engines, and in plasma cutting equipment, where its high melting point over 2,200 degrees is valuable. Interestingly, hafnium is chemically very similar to zirconium and almost always occurs alongside it in nature. Separating the two is extremely difficult, which kept hafnium undiscovered until 1923. The name comes from Hafnia, the Latin name for Copenhagen, where it was discovered. This obscure metal, twin to zirconium and named for a Scandinavian city, helps keep nuclear reactors safe and stable, absorbing the invisible particles that drive atomic energy. Zirconium is used to clad nuclear fuel rods. Zirconium, hafnium's chemical twin, has its own crucial role in nuclear reactors. While hafnium absorbs neutrons, zirconium does the opposite. It's nearly transparent to neutrons, allowing them to pass through with minimal absorption. This makes zirconium ideal for cladding nuclear fuel rods. The fuel in a nuclear reactor consists of pellets of uranium or other fissile material. These pellets must be contained in tubes that protect them from the reactor's harsh environment while allowing neutrons to flow freely. Zirconium alloys, particularly zircalloy, meet these requirements perfectly. Zirconium is also highly resistant to corrosion in the high-temperature water that cools most reactors. It maintains its strength and integrity under extreme conditions. Essentially, zirconium forms the protective skin around nuclear fuel, invisible to the neutrons that must reach the fuel to sustain reactions. Beyond nuclear applications, zirconium is used in chemical processing equipment, where corrosion resistance is essential. Cubic zirconia, a synthesized crystal form of zirconium oxide, serves as an inexpensive diamond simulant in jewelry. These clear crystals can look remarkably like diamonds, though they lack diamond's hardness and thermal properties. Zirconium's name comes from the Persian word zargun, meaning gold-colored, referring to zircon gemstones. From ancient gemstones to modern nuclear reactors, zirconium has traveled a long path. The metal that lets neutrons pass freely enables nuclear power while protecting us from the hazards within. Molybdenum helps enzymes function in living organisms. Molybdenum is a silvery metal with a name that's challenging to pronounce. It comes from the Greek molybdos, meaning lead-like, because molybdenum ores were confused with lead ores in ancient times. This hard, corrosion-resistant metal has a very high melting point, over 2,600 degrees, making it useful for high-temperature applications. Molybdenum is primarily used as an alloying element in steel. Molybdenum steel is exceptionally strong and resistant to corrosion, used in pipelines, aircraft parts, and high-pressure vessels. The metal is also used in furnace components, as electrodes, and in various chemical catalysts. But molybdenum has a softer side. It's an essential trace element for nearly all forms of life. In living organisms, molybdenum is a cofactor in enzymes, proteins that catalyze biochemical reactions. Molybdenum-containing enzymes are involved in nitrogen fixation, allowing certain bacteria to convert atmospheric nitrogen into forms usable by plants. Other molybdenum enzymes help break down purines and sulfur-containing amino acids in animals. In humans, molybdenum deficiency is rare because we need such tiny amounts, only about 45 micrograms per day. But without it, certain metabolic processes would fail. It's found in foods like legumes, grains, and nuts. The fact that this tough, heat-resistant industrial metal is also essential for life reminds us how chemistry connects the inanimate and the living. The same element, strengthening steel pipes, also enables enzymes that keep cells functioning. Niobium makes steel stronger and is used in MRI magnets. Niobium, formerly called columbium, is a shiny gray metal with impressive superconducting properties. When cooled to very low temperatures, niobium loses all electrical resistance, becoming a perfect conductor. This property makes niobium essential for superconducting magnets, particularly those in MRI machines. Magnetic resonance imaging, or MRI, uses powerful magnetic fields to create detailed images of the inside of the human body. The magnets in MRI machines must generate extremely strong, stable fields. Superconducting electromagnets, made with niobium titanium alloy wire, can achieve this while consuming minimal power. Once current is established in a superconducting coil, it can flow indefinitely without energy input, as long as the coil remains cold. Liquid helium cools these magnets to just a few degrees above absolute zero. Niobium's superconductivity makes this possible. The metal is also used in particle accelerators, like the Large Hadron Collider, where superconducting niobium cavities accelerate particles to near light speed. Beyond superconductivity, niobium is added to steel in small amounts to increase strength and toughness. Niobium steel alloys are used in pipelines, automotive parts, and structural applications. The element is named after Niobe, a figure from Greek mythology, daughter of Tantalus. Since niobium and tantalum are chemically similar and occur together, naming them after father and daughter seemed fitting. From ancient myth to modern medicine, from particle physics to pipelines, niobium connects diverse fields. The metal that conducts electricity without resistance helps us see inside bodies and probe the nature of matter itself. Praseodymium creates strong, permanent magnets. The rare earth elements, a group including the lanthanides on the periodic table, have names that can be tongue twisters. Praseodymium is no exception. The name comes from Greek words meaning green twin, referring to its green salts. Praseodymium itself is a soft, silvery metal that tarnishes in air to a green oxide coating. While not a household name, praseodymium plays a role in one of modern technology's most important materials, neodymium magnets. These powerful permanent magnets, more properly called neodymium iron-boron magnets, actually contain praseodymium as well. The addition of praseodymium improves the magnet's performance at high temperatures. These rare earth magnets are the strongest type of permanent magnet commercially available. They're found in countless devices: the motors in electric vehicles, wind turbine generators, computer hard drives, headphones, and even the vibration motor in smartphones. Their strength allows devices to be smaller and more efficient. Praseodymium is also used in specialized glasses and ceramics. When added to glass, it creates a yellow-green color used in welding goggles to filter out certain wavelengths. Praseodymium is used in carbon arc lights for film and television studios, creating a light that closely mimics sunlight. The metal is also part of the mischmetal alloy used in lighter flints, where its pyrophoric properties, meaning it sparks when scraped, create the familiar flame. From the magnets driving electric motors to the sparks lighting fires, praseodymium works quietly behind the scenes, a green twin supporting modern life. Samarium cobalt magnets work at higher temperatures than neodymium. While neodymium magnets are more widely known, samarium cobalt magnets hold their own important niche. These magnets, made from alloys of samarium and cobalt, were actually developed before neodymium magnets. They are nearly as strong and have a significant advantage. They maintain their magnetic properties at much higher temperatures. Neodymium magnets lose their magnetization if heated above around 80 to 200 degrees, depending on the grade. Samarium cobalt magnets can withstand temperatures exceeding 300 degrees, while remaining magnetic. This makes them essential for applications in high-temperature environments like jet engines, industrial motors, and downhole drilling equipment in oil and gas exploration. The magnets are also more resistant to corrosion than neodymium magnets, requiring no protective coating. Samarium itself is a silvery metal, part of the rare earth elements. It's named after samarskite, a mineral named after Russian mining engineer Vasily Samarsky-Bykovets. Samarium has other interesting properties. Some samarium isotopes are excellent neutron absorbers, used in nuclear reactor control rods, similar to hafnium. Samarium oxide is used in optical glass and ceramics. In medicine, radioactive samarium-153 is used to treat pain from bone cancer, as it concentrates in bone metastases and delivers localized radiation. From the heat of jet engines to the treatment of cancer, from oil wells to precision instruments, samarium works in extremes. The metal, named for a 19th century Russian engineer, enables 21st century technology. Europium makes red phosphors in older televisions glow. Before flat-screen TVs, cathode ray tube televisions dominated living rooms for decades. These TVs created color images by firing electron beams at phosphor-coated screens. Different phosphors emit different colors when struck by electrons. For the red component of the image, europium was often the key ingredient. Europium compounds, particularly europium oxide, doped into yttrium vanadate or yttrium oxide, produce a pure, bright red emission. This europium-activated phosphor created the red pixels, combining with green and blue phosphors to form full-color images. Europium is named after Europe, continuing the tradition of naming elements after places. It's one of the most reactive rare earth metals, tarnishing quickly in air. Pure europium has limited applications due to its reactivity, but its compounds are valuable for their luminescent properties. Beyond old televisions, europium is used in euro banknotes as an anti-counterfeiting measure. Under ultraviolet light, europium in the ink glows distinctively, helping verify authenticity. Europium is also used in fluorescent lamps, providing red emission to improve the quality of white light. Interestingly, europium is one of the rarest rare earth elements, despite the group as a whole not being particularly rare. Its scarcity and specific properties make it valuable. As technology has shifted from CRTs to LED and OLED displays, europium's role has diminished somewhat, but it remains part of some LED phosphors and continues its anti-counterfeiting work. The metal of Europe lit millions of screens and still helps protect currency. Gadolinium is used as a contrast agent in medical imaging. Gadolinium is a silvery white metal with unusual magnetic properties. It's one of only 4 elements that can be magnetic at room temperature, alongside iron, cobalt, and nickel. But gadolinium's magnetism is paramagnetic, meaning it's only magnetic in the presence of an external magnetic field. This property, combined with other characteristics, makes gadolinium valuable in medicine. Gadolinium-based contrast agents are used in magnetic resonance imaging, or MRI. When injected into patients, these compounds improve the visibility of internal structures in MRI scans. Gadolinium affects the behavior of nearby water molecules in magnetic fields, enhancing contrast between different tissues. This helps doctors detect tumors, inflammation, blood vessel abnormalities, and other conditions more clearly. The gadolinium itself isn't directly visible in the image, but its effects on surrounding hydrogen atoms are. Because free gadolinium ions are toxic, the metal is bound in complex molecules called chelating agents that hold it safely until it's eliminated from the body through the kidneys. For most patients, gadolinium contrast is safe, though people with severe kidney problems must avoid it due to risks of accumulation. Gadolinium is named after Johann Gadolin, a Finnish chemist who investigated rare earth elements. Beyond medicine, gadolinium is used in neutron radiography, a technique similar to X-ray but using neutrons. Gadolinium absorbs neutrons effectively, creating contrast. Gadolinium compounds are also used in some electronics and as phosphors, from revealing hidden tumors to absorbing neutrons. Gadolinium's magnetic personality serves humanity in unexpected ways. Dysprosium is essential for making powerful magnets for electronics. Dysprosium has a name meaning hard to get in Greek, reflecting the difficulty early researchers had isolating it. This silvery metal is one of the rare earth elements, and while not extremely rare in absolute terms, high-purity dysprosium is indeed challenging to obtain. Dysprosium's primary importance lies in its addition to neodymium magnets. Adding dysprosium to these magnets significantly improves their resistance to demagnetization at high temperatures. For neodymium magnets to function in hot environments, like electric vehicle motors or wind turbine generators, dysprosium is often essential. Even small additions, just a few percent, make a substantial difference. This has made dysprosium strategically important. As demand for electric vehicles and renewable energy technologies grows, so does demand for dysprosium. Concerns about supply have driven research into reducing dysprosium content in magnets or finding alternatives. Most dysprosium is produced in China, making it subject to geopolitical considerations. Dysprosium is also used in certain types of lasers and in nuclear reactor control rods, where its excellent neutron-absorbing properties are valuable. In specialized lighting applications, dysprosium iodide is used in metal halide lamps. The element's magnetic properties are also exploited in data storage and various electronic devices. The metal that was hard to get when discovered remains hard to get in the sense of being a limiting factor for emerging technologies. Dysprosium sits at an intersection of material science, clean energy, and global politics, a modest metal with an outsized role in the future. Holmium has the highest magnetic strength of any element. Among all elements, holmium holds a unique distinction. It has the highest magnetic moment of any naturally occurring element. This means that when placed in a magnetic field, holmium becomes more strongly magnetized than any other element. This property makes holmium valuable for creating the strongest possible magnetic fields in certain applications. Holmium is used in some of the most powerful artificial magnets, combining with other elements to create alloys with extraordinary magnetic strength. The element also has medical applications. Holmium lasers are used in surgery, particularly for procedures involving the prostate, kidney stones, and certain eye surgeries. The holmium YAG laser, which uses a crystal containing holmium, yttrium, aluminum, and garnet, produces laser light at a wavelength readily absorbed by water. Since human tissue contains much water, this laser can precisely cut or ablate tissue. The laser's energy vaporizes the water in cells, effectively destroying targeted tissue while minimizing damage to surrounding areas. Holmium oxide has a distinctive yellow color and is used in cubic zirconia and glass to give yellow or red coloration. In nuclear reactors, holmium is used in control rods as a burnable poison, a material that absorbs neutrons initially but is gradually depleted. The element is named after Holmia, the Latin name for Stockholm. continuing the tradition of naming rare earth elements after places. From the strongest magnets to precise surgical lasers, holmium demonstrates that obscure elements can have focused, powerful applications. The most magnetic element serves both industry and medicine. Erbium is used in fiber optic communications. The internet, streaming services, phone calls, all depend on data transmitted as light through fiber optic cables. These hair-thin glass fibers carry information encoded in laser pulses across continents and under oceans. But light traveling through glass gradually weakens over distance, a problem called attenuation. For long-distance transmission, the signal must be amplified. This is where erbium enters the story. Erbium-doped fiber amplifiers, or EDFAs, revolutionized fiber optic communications in the late 20th century. These devices consist of optical fiber that contains erbium ions. When light at a specific wavelength around 1500 nanometers, commonly used in telecommunications, passes through erbium-doped fiber and is simultaneously illuminated by a pump laser, the erbium ions absorb energy from the pump and transfer it to the signal light, amplifying it. This amplification happens directly in the optical domain, without converting light to electrical signals and back. EDFAs enabled the high-speed, long-distance optical networks that underpin modern telecommunications. Erbium is a soft, silvery metal, part of the rare earth elements. Its name comes from Ytterby, the Swedish village that gave its name to several rare earth elements. Beyond telecommunications, erbium is used in lasers, particularly erbium-doped, solid-state lasers used in medicine and dentistry. Erbium lasers are valued for their precision in cutting tissue with minimal thermal damage. Erbium oxide gives a pink color to glass and is used in some sunglasses and photographic filters. The metal that carries our messages through glass fibers connects the world, invisible but indispensable. Thulium is the rarest and most expensive rare earth element. Even among the rare earth elements, thulium stands out for its scarcity. It is the least abundant of the rare earths that occur naturally, though even rare earths aren't particularly rare compared to elements like gold or platinum. Thulium is more common than either, but extracting and purifying it is challenging and expensive. The element was named after Thule, an ancient name for Scandinavia, continuing the geographic naming tradition. Thulium is a silvery metal that slowly tarnishes in air. Its scarcity means it has limited commercial applications, though its unique properties have found some uses. Thulium has been used in portable X-ray devices. Thulium-170, a radioactive isotope, can be used as a radiation source for portable X-ray units. These are useful in medical and industrial applications where conventional X-ray machines are impractical. Thulium is also used in certain lasers, particularly thulium fiber lasers used in medical procedures and material processing. These lasers are efficient and produce wavelengths that are readily absorbed by tissue and other materials. Thulium has been used in euro banknotes as part of anti-counterfeiting measures, emitting a distinctive color under ultraviolet light. In research settings, thulium's magnetic and spectroscopic properties make it useful for studies in physics and chemistry. The rarest of the rare earths, thulium occupies a small niche. Its applications are specialized, its production limited, yet even the rarest elements find their purposes, serving needs that more common materials cannot meet. Thulium reminds us that scarcity can create value in unexpected ways. Ytterbium is used in atomic clocks and laser technology. Ytterbium, yet another element named after the Swedish village of Ytterby, is a soft, malleable metal with several important modern applications. Like other rare earth elements, ytterbium is silvery when freshly cut, but tarnishes quickly in air. This element has found its way into some of the most precise measurement devices ever created: atomic clocks. Yttrium-based atomic clocks are among the most accurate timekeeping devices known. These optical lattice clocks use laser-cooled yttrium atoms trapped in an optical lattice formed by intersecting laser beams. By measuring the frequency of light absorbed or emitted by these atoms as they transition between energy levels, scientists can define time with extraordinary precision. These clocks are so accurate, they would lose less than a second over the age of the universe. Such precision might seem excessive, but it has practical implications. Better clocks improve GPS accuracy, enable better scientific experiments, and could one day help detect gravitational waves more effectively, or search for variations in fundamental constants. Ytterbium is also used in industrial lasers, particularly ytterbium-doped fiber lasers. These lasers are efficient, powerful, and reliable, used for cutting and welding metals in manufacturing. Ytterbium compounds are used in stainless steel, in certain medical treatments, and as catalysts in organic chemistry. The element has even been used in experimental earthquake prediction, as ytterbium alloys can detect minute changes in stress. From measuring time with unprecedented precision to cutting steel with light, ytterbium demonstrates versatility. The metal from ytterbium keeps pace with time itself. Lutetium is the last lanthanide and very dense. Lutetium closes out the lanthanide series, the rare earth elements spanning from lanthanum to lutetium on the periodic table. It's the heaviest and hardest of the rare earths, with a density nearly as high as gold. The element's name comes from Lutetia, the ancient Roman name for Paris, as the discoverer worked in France. Lutetium is a silvery white metal that is relatively stable in air compared to other rare earths, though it still tarnishes slowly. For many years, lutetium was considered the least useful of the rare earth elements. Its scarcity and expense, combined with a lack of unique properties, meant few applications existed. However, modern technology has found uses for this once overlooked element. Lutetium is used in positron emission tomography, or PET scans. Lutetium oxyorthosilicate, or LSO, is a scintillator material used in PET detectors. When struck by gamma rays, it emits visible light that can be detected and used to create images. LSO's high density and fast response make it ideal for this application, helping doctors diagnose cancer and other conditions. Lutetium is also used in certain petroleum refining catalysts and in materials for LEDs. Lutetium aluminum garnet, or LUAG, is used as a host material for phosphors in white LEDs. Radioactive lutetium-177 is being investigated for cancer treatment, as it can be targeted to tumors and deliver localized radiation therapy. The last of the lanthanides, once thought least useful, has found its calling in medicine. Lutetium helps us see inside bodies and may help treat the diseases it reveals. Scandium makes aluminum alloys lighter and stronger. Scandium is the lightest rare earth element, though its classification as a rare earth is sometimes debated since it's not a lanthanide. Regardless of categorization, scandium is notable for its effects on aluminum alloys. Adding small amounts of scandium to aluminum, typically less than 1%, creates alloys with remarkable properties. Scandium aluminum alloys are significantly stronger than regular aluminum while remaining light. The scandium refines the grain structure of the aluminum, making it more resistant to cracking and more easily welded. These properties make scandium aluminum alloys attractive for aerospace applications. Some high-performance aircraft use scandium aluminum components where weight savings and strength are both critical. Scandium aluminum alloys are also used in sporting goods, high-end bicycle frames, baseball bats, and other equipment benefit from the material's light weight and durability. The element has been used in metal halide lamps, producing light with good color rendering properties. Scandium iodide lamps are used in film and television production, where accurate color reproduction is important. Despite these valuable applications, scandium remains one of the more expensive rare earth elements. It's actually reasonably abundant in Earth's crust, more common than lead, but it's widely dispersed rather than concentrated in easily mined deposits. Extracting scandium economically remains challenging. Most scandium is obtained as a byproduct from other mining operations. The element is named after Scandinavia, continuing the tradition of honoring places in element names. Scandium's potential to create better aluminum alloys means research continues into more efficient extraction methods. The light metal from Scandinavia makes our materials lighter still. Platinum resists corrosion better than almost any metal. Platinum's resistance to corrosion is legendary. This silvery white metal can withstand exposure to most acids, including the fearsome aqua regia that dissolves gold. Only a few extremely aggressive chemical environments can attack platinum. This extraordinary stability makes platinum invaluable in applications requiring long-term durability in harsh conditions. Platinum's primary use is in catalytic converters, as mentioned earlier, but its role extends far beyond. In chemistry laboratories, platinum crucibles and electrodes are standard equipment because they don't react with most chemicals, even at high temperatures. Platinum resistance thermometers are among the most accurate temperature sensors available, maintaining stable electrical properties over wide temperature ranges. The element is used in fuel cells, where it catalyzes the reactions that produce electricity from hydrogen and oxygen. Platinum jewelry is prized not only for its beauty, but for its durability and hypoallergenic properties. It doesn't tarnish or fade, maintaining its luster indefinitely. Platinum's density gives jewelry a satisfying weight. Platinum is also used in certain cancer chemotherapy drugs. Cisplatin and related compounds contain platinum atoms bonded to other groups. These drugs interfere with DNA replication in cancer cells. The metal's stability allows it to reach tumors intact before releasing its effect. In World War II, platinum was considered so strategically important that its use in jewelry was banned in the United States. All available platinum diverted to military applications. The metal that resists corrosion has proven itself resistant to obsolescence, finding new uses across centuries. Iridium is extremely hard and corrosion-resistant. Iridium shares platinum's resistance to corrosion, but takes it even further. This dense, silvery metal is nearly immune to chemical attack. It's also the most corrosion-resistant element known and one of the densest, competing with osmium for the title of densest element. Iridium's name comes from Iris, the Greek goddess of rainbows, because its salts are colorful, but there's nothing delicate about iridium itself. It's hard, brittle, and exceptionally difficult to work with. This combination of hardness and corrosion resistance makes iridium valuable for applications requiring ultimate durability. Iridium is used in spark plugs for aircraft and racing vehicles, where its ability to withstand extreme temperatures and resist erosion from electrical discharges extends service life. Osmium-iridium alloys, mentioned earlier, create fountain pen nibs that last for generations. Iridium is used in crucibles for growing large, high-quality crystals, as it can withstand the extreme temperatures and chemical environments involved. The element played a crucial role in the historical definition of the kilogram. For over a century, the international prototype kilogram, the physical object that defined the unit of mass, was made of a platinum-iridium alloy. This choice ensured stability over time, though in 2019, The kilogram was redefined using physical constants rather than a physical artifact. Interestingly, iridium is famous in another context. A layer of iridium-rich clay found worldwide marks the boundary between the Cretaceous and Paleogene periods, about 66 million years ago. This iridium anomaly is evidence of the asteroid impact that contributed to the extinction of dinosaurs. Iridium is rare on Earth's surface, but common in asteroids, so finding a global layer of it suggests a massive impact. The hardest, most corrosion-resistant metal carries the signature of Earth's most catastrophic extinction. Rhodium is the most expensive precious metal. When people think of valuable metals, gold and platinum come to mind, but rhodium, another platinum group metal, often exceeds both in price. Rhodium's value has fluctuated dramatically, sometimes reaching over 10 times the price of gold per ounce. This silvery white metal is extremely rare, with annual production measured in just tens of tons worldwide. Rhodium's primary use is in catalytic converters, where it works alongside platinum and palladium to reduce nitrogen oxide emissions from vehicles. Stricter emissions standards have driven up demand for rhodium, contributing to its high price. The metal is also used for plating, jewelry, and other items, providing a reflective, hard, and tarnish-resistant surface. White gold and sterling silver jewelry are often rhodium-plated to enhance their appearance and protect them from tarnish. Rhodium's reflectivity makes it valuable for mirrors in specialized applications. Rhodium-coated optics are used in high-intensity lighting systems and certain scientific instruments. The metal is also used in some chemical processes as a catalyst. Rhodium is named from the Greek word rhodon, meaning rose, because some rhodium compounds have a rosy color. The discovery of rhodium is credited to William Hyde Wollaston, who isolated it from platinum ore in 1803. The same chemist discovered palladium. Today, rhodium's rarity and essential role in emissions control keep it among the most valuable materials on Earth. The rose-colored compounds led to a metal worth its weight many times over in gold, a treasure hidden in plain sight in every catalytic converter. Ruthenium may be used in future computer chips. Ruthenium is a hard, silvery metal from the platinum group. Its name comes from Ruthenia, the Latin word for Russia, where the ore from which it was first isolated was found. For years, ruthenium was primarily a laboratory curiosity and a minor component in some platinum alloys. But modern technology is giving ruthenium new importance, particularly in electronics. As computer chips become smaller and more complex, the materials used in them must meet increasingly demanding requirements. Copper, the traditional material for connecting transistors on chips, faces limitations as features shrink. Copper atoms can migrate, causing short circuits and reliability issues. Ruthenium is being explored as a potential replacement or complement to copper in advanced chips. Ruthenium's electrical properties, resistance to electromigration, and ability to form thin, smooth films make it promising for next-generation semiconductors. Some manufacturers are already incorporating ruthenium into certain chip structures. Ruthenium is also used in certain hard disk drive coatings, where a thin layer of ruthenium-based material provides magnetic properties needed for data storage. In chemistry, ruthenium catalysts enable various important reactions. Ruthenium-based drugs are being investigated for cancer treatment, offering potential advantages over platinum-based chemotherapy. Ruthenium even has a role in solar technology. Ruthenium-based dyes are used in dye-sensitized solar cells, an alternative to traditional silicon panels. From Russia to the cutting edge of computing, ruthenium's journey continues. The metal that seemed obscure may soon be integral to the computers processing these very words. Manganese is essential for steel production and batteries. Manganese is a hard, brittle, silvery metal that most people haven't heard of. Yet it's the 12th most abundant element in Earth's crust and crucial to modern industry. Nearly 90% of manganese produced goes into steel manufacturing. Adding manganese to steel improves its strength, hardness, and resistance to wear. It also helps remove oxygen and sulfur during the steel-making process, improving quality. Almost all steel contains at least a small amount of manganese. High manganese steels, containing around 10 to 14% manganese, are incredibly tough and work-hardening, meaning they become harder when subjected to impact or stress. These steels are used in demanding applications like railroad switches, rock crushers, and armor plating. Beyond metallurgy, manganese is essential for living organisms. The element is a cofactor in several crucial enzymes. In plants, manganese is vital for photosynthesis, helping split water molecules to release oxygen. Manganese deficiency in crops can significantly reduce yields. In humans, manganese is needed for bone formation, blood clotting, and reducing inflammation. The metal also plays a growing role in energy storage. Alkaline batteries, the standard disposable batteries in many devices, use manganese dioxide in their cathodes. Rechargeable lithium-ion batteries increasingly use lithium manganese oxide or other manganese-containing cathodes. These materials are cheaper and potentially safer than some alternatives. As battery technology evolves, manganese's role is expanding. The unsung metal in every piece of steel may become equally essential in the batteries powering our electric future. From construction beams to the cells in our devices, manganese shapes our world. Cobalt is critical for rechargeable lithium-ion batteries. Cobalt has appeared earlier in our story for its beautiful blue pigments, but its modern importance lies largely in batteries. Most lithium-ion batteries, the rechargeable power sources in smartphones, laptops, and electric vehicles, contain cobalt in their cathodes. Lithium cobalt oxide was one of the first commercially successful cathode materials for lithium-ion batteries. It offers high energy density, meaning batteries can store substantial energy in a compact, lightweight package. For portable devices, this property is invaluable. As electric vehicles have grown more common, demand for cobalt has surged. A single electric vehicle battery can contain several kilograms of cobalt. However, cobalt presents challenges. It's relatively expensive, and much of the world's supply comes from the Democratic Republic of Congo, where mining conditions and ethical practices have raised concerns. Child labor and unsafe working conditions in some cobalt mines have prompted calls for responsible sourcing and certification. These challenges have driven research into reducing or eliminating cobalt from batteries. Some newer battery chemistries use less cobalt or substitute other materials like manganese and nickel. Tesla and other manufacturers have announced efforts to develop cobalt-free batteries. Despite these efforts, cobalt remains central to current battery technology. The same metal that created brilliant blues in ancient pottery now powers modern mobility. From pigments to power, cobalt's journey reflects changing technological needs. The element that once colored glass now electrifies transportation, carrying both promise and ethical complexity into the future. Selenium is a metalloid used in photocells and glass. Selenium occupies an interesting position between metals and non-metals. Classified as a metalloid, it can exist in several forms or allotropes. Gray selenium, the most stable form, has a metallic appearance and some metallic properties, though it's a poor conductor compared to true metals. Red selenium is a powder that looks nothing like metal. This chameleon element was named after Selene, the Greek goddess of the moon, as a companion to Tellurium, named after Earth. Selenium's most famous property is its photoconductivity. In darkness, selenium is a poor conductor of electricity, but when light strikes it, its conductivity increases dramatically. This property led to selenium's use in early photocells, light meters, and photocopiers. Though largely replaced by silicon in modern devices, selenium played a crucial historical role in developing photoelectric technology. Selenium is also used in glassmaking. Adding selenium to glass can create a pink or red color, or it can be used to decolorize glass, counteracting the greenish tint from iron impurities. Selenium is essential for living organisms in trace amounts. It's a component of certain enzymes with antioxidant functions. Brazil nuts are particularly rich in selenium. However, the line between sufficient and toxic is narrow. Too much selenium causes selenosis, with symptoms including hair loss, nail brittleness, and neurological problems. In electronics, selenium rectifiers were once common, converting alternating current to direct current. Though obsolete now, millions of these devices powered equipment for decades. From copying documents to coloring glass, from nutrition to early electronics, selenium's diverse roles reflect its dual nature, neither fully metal nor fully non-metal, but something in between. Tellurium makes steel and copper more machinable. Tellurium is another metalloid, similar to selenium but heavier and rarer. Its name comes from the Latin tellus, meaning earth. Tellurium has a silvery appearance when pure, though it often appears as a dark grey powder. This element is one of the rarest stable elements in Earth's crust, about as scarce as platinum. Despite its scarcity, tellurium has important applications. One of tellurium's primary uses is improving the machinability of metals. Adding small amounts of tellurium to steel or copper alloys makes them easier to machine. The tellurium forms tiny inclusions that act as chip breakers, causing metal to fracture cleanly during cutting operations, rather than forming long, stringy chips. This allows higher machining speeds and longer tool life. Tellurium copper alloys are particularly valuable for producing precise parts on high-speed automated equipment. Tellurium is also used in certain thermoelectric materials, substances that can convert heat directly into electricity, or vice versa. Bismuth telluride is one of the most common thermoelectric materials, used in solid-state cooling and power generation applications. These devices have no moving parts, making them reliable for specialized uses. In metallurgy, tellurium is added to lead to improve its strength and acid resistance, creating alloys used in chemical equipment and certain battery plates. Tellurium is used in some solar panels, particularly cadmium telluride thin-film solar cells, which offer a cost-effective alternative to silicon in certain applications. Interestingly, exposure to tellurium causes a distinctive garlic-like odor on the breath, as the body metabolizes it into dimethyl telluride. Workers in tellurium processing plants can recognize each other by this telltale sign. The earth element, rare and overlooked, quietly improves manufacturing and converts heat to electricity. Arsenic has a dark history, but useful applications. The word arsenic conjures images of poisonings and mystery novels. This element has indeed been used as a poison throughout history, earning a sinister reputation. Arsenic compounds are toxic because they interfere with cellular metabolism, particularly ATP production. Acute arsenic poisoning causes severe gastrointestinal symptoms, while chronic exposure leads to various cancers and other health problems. In the Victorian era, arsenic was so commonly used in murder that it was called inheritance powder. However, arsenic is more than its dark legacy. This metalloid, which can appear gray and metallic, or yellow and non-metallic, depending on its form, has legitimate applications. Arsenic compounds are used in semiconductors. Gallium arsenide, mentioned earlier, is used in high-speed electronics, LEDs, and solar cells. Indium gallium arsenide is used in infrared detectors. These compounds are stable and not bioavailable like pure arsenic, making them safe in contained applications. Historically, arsenic compounds were used in pigments, creating vivid greens like Paris green and Scheele's green. These pigments, popular in the 19th century for wallpaper, fabrics, and paint, may have contributed to numerous poisonings, including possibly Napoleon Bonaparte's, though this remains debated. Arsenic was also used in medicine, despite its toxicity. Fowler's solution, containing potassium arsenite, was used to treat various ailments. Salvarsan, an arsenic compound, was the first effective treatment for syphilis. Modern medicine still uses arsenic trioxide to treat certain types of leukemia. Arsenic even has a role in agriculture. Organic arsenic compounds were used in poultry feed to prevent disease and improve growth, though this practice has been banned or phased out in many regions. The poison that haunts history has, paradoxically, also healed and enabled technology, a reminder that context and dose determine whether a substance harms or helps. Technetium is the first human-made element. Of all the elements on the periodic table, technetium holds a unique place. It is the lightest element that does not occur naturally in any significant quantity on Earth. Every atom of technetium that exists today has been created by humans or arrives from space in cosmic rays. The element's name reflects this, derived from the Greek teknetos, meaning artificial. In 1937, technetium became the first element to be artificially produced, filling a gap in the periodic table. Scientists had long noticed the absence of elements 43 and 61. Element 43 was created by bombarding molybdenum with deuterons in a cyclotron. This achievement proved that elements could be synthesized, not just discovered. Technetium is radioactive, with no stable isotopes. Its most stable isotope, technetium-98, has a half-life of over 4 million years. Despite its radioactivity and artificial nature, technetium has found important applications. The isotope technetium-99m, where M stands for metastable, is widely used in nuclear medicine. It's the most common radioactive tracer for diagnostic imaging. Technetium-99m has a convenient 6-hour half-life, long enough to perform scans, but short enough that radioactivity decays quickly afterward. It emits gamma rays that imaging equipment can detect, allowing doctors to visualize organs and tissues. Millions of medical procedures use technetium-based imaging each year. Technetium's radioactive properties have limited other applications, though it has been used in corrosion protection research. The fact that this artificial element has saved countless lives through medical imaging is a testament to human ingenuity. From cyclotrons to clinics, technetium bridges nuclear physics and medicine. Polonium is one of the most radioactive elements. Polonium is infamous as one of the most toxic and radioactive substances known. This metal, with no stable isotopes, was discovered by Marie and Pierre Curie in 1898. Marie named it after her native Poland, making a political statement as Poland was then partitioned and erased from maps. Polonium-210, the most common isotope, has a half-life of just over 138 days. Despite this brief existence, it's extraordinarily dangerous. Polonium is an alpha emitter, meaning it releases alpha particles, helium nuclei. Alpha particles don't penetrate deeply, stopped even by paper or skin. But if polonium is inhaled, ingested, or enters the body through a wound, it delivers devastating internal radiation. A single microgram of polonium, a barely visible speck, can be lethal. Polonium's intense radioactivity causes it to glow faintly blue in the dark, and any container holding it becomes warm from the energy released. This property led to one of polonium's few applications: heat sources in spacecraft. Early space missions used polonium-fueled radioisotope heaters to keep instruments warm in the cold of space. However, the short half-life means the material must be constantly replenished, limiting practicality. Polonium gained notoriety in 2006 when it was used to poison former Russian spy Alexander Litvinenko in London. The assassination highlighted polonium's extreme toxicity and the sophistication required to obtain and handle it. Beyond murder and mayhem, polonium has limited uses in anti-static devices and as initiators in some nuclear weapons. The element named for a vanished nation carries death in microscopic doses, a reminder of radioactivity's terrible power. Francium is the most unstable naturally occurring element. At the bottom of the first column of the periodic table, below cesium, lies francium. This metal is extraordinarily rare and incredibly unstable. Francium is the most unstable element that occurs naturally, with its longest-lived isotope, francium-223, having a half-life of just 22 minutes. Most isotopes decay in less than a second. This extreme instability means that at any given time, only about 20 to 30 grams of francium exist in the entire Earth's crust. It forms as a radioactive decay product of actinium and itself decays almost immediately into other elements. Francium has never been isolated in visible quantities. The metal's properties are mostly theoretical, inferred from its position on the periodic table and from studying atoms in gas phase. It's predicted to be highly reactive, even more so than cesium. If enough francium could be gathered, which is impossible due to its decay, it would react explosively with water and probably with air. The heat from its own radioactive decay would likely vaporize any sample. Francium was discovered in 1939 by Marguerite Perry in France, and she named it after her homeland. Because of its scarcity and instability, francium has no applications beyond research. Scientists have studied individual francium atoms to understand atomic structure and test theories in physics. The element serves as a reminder that not all matter is stable or long-lived. Francium, the phantom metal, exists only fleetingly, a temporary arrangement of protons, neutrons, and electrons that dissolves almost as soon as it forms. Even in nature's variety, some combinations are too unstable to endure. Calcium is the most abundant metal in the human body. When we think of metals in our bodies, we might imagine trace amounts, barely measurable quantities serving obscure functions. But calcium defies this expectation. This soft, silvery alkaline earth metal is the fifth most abundant element in the human body and the most abundant metal. An average adult human contains about 1 to 1.2 kilograms of calcium, with more than 99% of it in bones and teeth. Calcium provides the structural rigidity that allows us to stand, move, and protect our internal organs. Bones are essentially calcium phosphate crystals embedded in a protein matrix. This combination creates a material that's both strong and slightly flexible. Teeth, which must withstand tremendous forces during chewing, are similarly composed of calcium-based minerals, primarily hydroxyapatite. But the remaining 1% of calcium, dissolved in blood and other fluids, is equally vital. Calcium ions are essential for muscle contraction, including the heart. They play a crucial role in nerve signal transmission, allowing your brain to communicate with your body. Calcium is necessary for blood clotting, preventing excessive bleeding from injuries. It's involved in cellular signaling, helping cells respond to their environment. Despite its importance, the body cannot produce calcium. We must obtain it through diet, from sources like dairy products, leafy greens, and fortified foods. If dietary calcium is insufficient, the body extracts it from bones, weakening them over time. This is why calcium deficiency, especially during growth periods or aging, can lead to osteoporosis and fractures. Pure calcium metal is reactive, tarnishing quickly in air and reacting with water. But, in its ionic form, bound in compounds, calcium literally holds us together, a metal framework beneath flesh, enabling every movement and thought. Barium is used in medical imaging of the digestive system. Barium is a soft, silvery, alkaline earth metal that reacts readily with air and water. In its pure form, it's quite reactive and must be stored carefully. But barium compounds have found an important medical application. Barium sulfate, a white powder that is insoluble in water and body fluids, is used as a contrast agent in X-ray imaging of the digestive system. X-rays pass easily through soft tissues, making them appear similar on radiographs. Bones, being dense and containing calcium, block X-rays and show up clearly. But the stomach, intestines, and other digestive organs are difficult to visualize. This is where barium sulfate enters. Patients drink a barium sulfate suspension, often called a barium meal or barium swallow, or it's administered as an enema. The barium coats the lining of the digestive tract. Because barium is dense and blocks X-rays, the coated organs show up clearly on radiographs. This allows doctors to see the shape and function of the esophagus, stomach, and intestines, identifying ulcers, tumors, strictures, and other abnormalities. Barium sulfate's lack of solubility is crucial. Soluble barium compounds are toxic, as barium ions interfere with cellular processes, particularly muscle function. Barium poisoning can cause heart problems, paralysis, and death. But barium sulfate remains inert as it passes through the digestive system, making it safe for patients. After the examination, the body eliminates the barium naturally. Beyond medicine, barium compounds are used in oil and gas drilling fluids, as pigments providing brightness in paints and papers, and in fireworks, where barium creates brilliant green colors. The reactive metal that must be handled with care becomes a diagnostic tool that illuminates hidden ailments, helping doctors see what the eye cannot. Strontium creates brilliant red colors in fireworks. When fireworks burst across the night sky in deep, brilliant red, you're likely seeing strontium at work. This soft, silvery, alkaline earth metal, when heated, emits intense red light at specific wavelengths. Strontium compounds, particularly strontium carbonate and strontium nitrate, are the primary chemicals used to create red in fireworks and flares. The element was discovered in the Scottish village of Strontian, from which it takes its name. Strontium is chemically similar to calcium and barium, sitting between them on the periodic table. Like them, it's reactive and never found in pure form in nature. Strontium occurs in minerals like celestite and strontianite. Beyond fireworks, strontium has other applications. Strontium oxide was historically used in cathode ray tube television screens, where it absorbed X-rays produced inside the tubes, protecting viewers. Though CRT TVs are largely obsolete, millions of old sets still contain strontium. Strontium is also used in certain glasses and ceramics. Strontium titanate is used in synthetic gemstones, sometimes called fabulite, which have brilliance exceeding diamonds, though they lack diamond's hardness. Radioactive strontium-90, a byproduct of nuclear fission, is unfortunately well known. Released during nuclear accidents and weapons testing, strontium-90 is hazardous because it chemically resembles calcium. The body incorporates it into bones, where it delivers damaging radiation. This isotope was a major concern during the Cold War era of atmospheric nuclear testing. Today, that red glow in holiday fireworks is a safer side of strontium, a metal that can create beauty or danger depending on which isotope and how it's used. The element from a small Scottish village lights up celebrations worldwide. Rubidium ignites spontaneously in air. Rubidium sits below potassium in the alkali metal column, and like its relatives, it's highly reactive. In fact, rubidium is so reactive that it ignites spontaneously when exposed to air. It must be stored under oil or in vacuum-sealed containers. The metal is soft, with a silvery appearance when freshly cut, but tarnishes almost instantly as it reacts with moisture and oxygen. If you were to drop rubidium into water, the reaction would be violent, similar to cesium, though slightly less explosive. Rubidium's name comes from the Latin rubidus, meaning deepest red. When vaporized in a flame, rubidium produces a distinctive red-violet color, which is how it was discovered spectroscopically in 1861. Despite its reactivity, or perhaps because of its unique properties, rubidium has found modern applications. Rubidium is used in atomic clocks, though less commonly than cesium. Rubidium clocks are smaller and less expensive than cesium clocks, while still offering excellent accuracy. They're used in telecommunications and GPS systems. Rubidium vapor is used in magnetometers, devices that measure magnetic field strength, useful in mineral exploration and submarine detection. Perhaps most excitingly, rubidium was used to create the first Bose-Einstein condensate in 1995. By cooling rubidium atoms to temperatures within a millionth of a degree above absolute zero, scientists created a new state of matter where atoms lose their individual identities and behave as a single quantum entity. This achievement earned the Nobel Prize in Physics in 2001. Rubidium has also been investigated for biomedical imaging and as a potential treatment for depression, as it may have mood-stabilizing properties similar to lithium. The metal that bursts into flame in air has helped us understand the quantum realm and keeps our communications synchronized. From Victorian spectroscopes to quantum mechanics, rubidium's journey continues. Potassium reacts vigorously with water and produces purple flames. Potassium is an alkali metal, soft enough to cut with a knife and highly reactive. In nature, potassium is always found in compounds, never as pure metal. When isolated, potassium has a silvery appearance, but tarnishes within seconds in air. The metal reacts violently with water, producing hydrogen gas and potassium hydroxide. The reaction generates enough heat to ignite the hydrogen, producing a distinctive lilac or light purple flame. This flame color is so characteristic that it's used to identify potassium in qualitative analysis. Potassium's reactivity means it must be stored under oil or in an inert atmosphere. Despite the danger of pure potassium, its compounds are essential for life. Potassium ions are crucial for nerve function, muscle contraction, and maintaining proper fluid balance in cells. Along with sodium, potassium creates the electrical gradients that allow neurons to transmit signals. Your heart's rhythm depends on carefully balanced potassium levels. Too much or too little can cause cardiac problems. We obtain potassium from foods like bananas, potatoes, spinach, and beans. Potassium compounds have many uses. Potassium chloride is used as a fertilizer, providing an essential nutrient for plant growth. It's also used as a salt substitute for people limiting sodium intake. Potassium carbonate, or potash, is used in glass making, soap production, and various chemical processes. Potassium nitrate is a component of gunpowder and some fertilizers. Historically, potash was so valuable that it drove exploration and trade. The element's name comes from potash, which was extracted from wood ashes in large pots. From the purple flames of its reaction to the electrical signals in our nerves, potassium connects chemistry and biology. The metal that explodes in water is essential for the water-based life within us. Every metal has a unique crystalline structure. When you hold a piece of metal, it feels solid and uniform. But at the atomic level, metals are highly organized. The atoms arrange themselves in repeating three-dimensional patterns called crystal lattices. Each metal adopts a specific structure, or sometimes multiple structures depending on temperature and pressure. These atomic arrangements determine many of the metal's properties. Iron, for example, exists in different crystal structures at different temperatures. At room temperature, it adopts a body-centered cubic structure, where atoms sit at the corners of a cube with one atom at the center. When heated above about 900 degrees, iron transforms to a face-centered cubic structure, with atoms at the cube corners and centers of each face. This transformation affects iron's magnetic properties and its ability to dissolve carbon, which is crucial for steel production. Copper, silver, and gold all share the face-centered cubic structure, contributing to their similar ductility and conductivity. Zinc and magnesium adopt hexagonal, close-packed structures, where atoms are arranged in tightly packed hexagonal layers. This structure makes these metals more prone to specific types of deformation. Understanding crystal structures allows metallurgists to predict and control how metals behave. Heat treatments, alloying, and mechanical working can manipulate these structures, creating materials with desired properties. The grain structure within a metal, how different crystal regions are oriented, also affects strength and durability. Under a microscope, polished and etched metal surfaces reveal these grains, looking like a map of tiny territories. Each shiny piece of metal is not uniform but a complex landscape of crystals, invisibly organized, giving the material its character. Metals are excellent conductors because of free electrons. Why do metals conduct electricity and heat so well? The answer lies in their electronic structure. In most materials, electrons are tightly bound to atoms, unable to move freely. But in metals, something special happens. The outermost electrons of metal atoms are loosely held, able to detach and move throughout the material. These are called conduction electrons, or free electrons. They form what's sometimes described as an electron sea, surrounding the positively charged metal ions. When you apply an electrical voltage across a metal, these free electrons drift toward the positive terminal, creating an electrical current. The abundance of mobile electrons means metals can carry large currents with relatively little resistance. This is why copper and aluminum are used for electrical wiring. The same free electrons also conduct heat. When one end of a metal rod is heated, the electrons there gain energy and move faster. As they travel through the material, they collide with other electrons and atoms, transferring energy. This allows heat to spread quickly through metals, much faster than in non-metallic materials where heat must be transferred through slower molecular vibrations. Different metals conduct with different efficiency. Silver is the best electrical conductor, followed closely by copper, gold, and aluminum. Factors like crystal structure, purity, and temperature affect conductivity. As temperature increases, atoms vibrate more, scattering electrons and increasing resistance. This is why superconductors, which have zero resistance, only work at very low temperatures. The mobile electrons that make metals shiny also make them conductive. It's all connected through the unique way metals hold their electrons, loosely enough to share, tightly enough to remain solid. Alloys combine metals to create superior properties. Pure metals have useful properties, but often they can be improved. Combining two or more metals creates an alloy, a material with characteristics different from any of its components. Humanity has been creating alloys for millennia, often by accident. Bronze, the copper-tin alloy mentioned earlier, was perhaps the first deliberate alloy, launching an entire age of civilization. Steel, iron alloyed with carbon and sometimes other elements, transformed construction and manufacturing. Stainless steel adds chromium for corrosion resistance. Adding small amounts of other metals creates specialized steels for every conceivable application. Aluminum alloys combine aluminum with copper, magnesium, manganese, silicon, or other elements. Pure aluminum is soft and weak. Alloyed aluminum can be strong, hard, and still lightweight, suitable for aircraft and vehicles. Brass and bronze offer variations on copper, each with distinct properties. Superalloys, complex combinations designed for extreme conditions, can withstand temperatures and stresses that would destroy pure metals. Nickel-based superalloys power jet engines, operating at temperatures where the metal glows red yet maintains strength. The science of creating alloys involves understanding how different atoms interact when mixed. Some elements dissolve into each other, creating solid solutions. Others form distinct phases, separate structures within the material. Heat treatment can change these internal structures, further modifying properties. The proportions matter. Adding 1% of an element might have little effect, while 5% could transform the material. It's a subtle art backed by rigorous science. Every metal object around you is likely an alloy, carefully formulated. The steel in buildings, the aluminum in beverage cans, the gold in jewelry, all are mixtures, perfected through centuries of experimentation. Purity, it turns out, is often less useful than thoughtful combination. Shape memory alloys remember their original form. Some alloys have a seemingly magical property. Deform them, twist them into a new shape, and they spring back to their original form when heated or when the stress is removed. These are shape memory alloys, or SMAs, and they have unique applications. The most common shape memory alloy is nitinol, an alloy of nickel and titanium. Nitinol can be bent or stretched significantly. Then, when heated above a certain temperature, it returns to its preset shape. This transformation occurs because the alloy exists in two different crystal structures at different temperatures. The low-temperature form is easily deformed. When heated, it transforms to the high-temperature form, which snaps back to its memory shape. Shape memory alloys are used in medical devices. Nitinol stents, tiny mesh tubes used to keep blood vessels open, can be compressed for insertion through a catheter. Once positioned, body heat causes them to expand to their preset size, holding the vessel open. Orthodontic braces use nitinol wires that exert constant, gentle pressure as they try to return to their original shape, gradually moving teeth. Beyond medicine, SMAs find use in eyeglass frames that are durable and flexible, in actuators that move when heated, and in aerospace applications. Some concepts explore using shape memory alloys in adaptive aircraft wings that change shape in flight. The alloys can also demonstrate superelasticity, able to undergo large deformations and recover without heating, making them ideal for applications requiring flexibility and resilience. These metals that remember offer a glimpse of responsive materials that can adapt and react, blurring the line between passive material and active component. Some metals become superconductors at very low temperatures. In 1911, Dutch physicist Heike Kamerlingh-Ons made a startling discovery. When he cooled mercury to just 4 degrees above absolute zero, its electrical resistance vanished completely. Current flowing through the mercury continued indefinitely without any applied voltage. This was superconductivity, one of the most remarkable phenomena in physics. Many metals and alloys become superconductors at sufficiently low temperatures, though the transition temperature varies. For most elemental metals, superconductivity requires temperatures below about 10 degrees above absolute zero, achievable only with liquid helium. This limitation restricted practical applications for decades. Superconductors have 2 key properties. Zero electrical resistance means current flows without energy loss. Perfect diamagnetism, called the Meissner effect, means superconductors expel magnetic fields, causing magnets to levitate above them. This levitation is visually striking and has practical implications. The search for high-temperature superconductors, materials that superconduct at more accessible temperatures, has been ongoing. Discoveries of ceramic compounds that superconduct above liquid nitrogen temperature, 77 degrees above absolute zero, enabled broader applications. Superconducting magnets in MRI machines, particle accelerators, and magnetic levitation trains rely on these materials. Superconductivity arises from quantum mechanical effects. At low temperatures, electrons in the material pair up and move cooperatively, no longer scattering off impurities or vibrations that normally create resistance. This electron pairing allows the resistance-free current flow. Research continues into room temperature superconductors. In 2020, a material was reported to superconduct at 15 degrees centigrade, but only under extremely high pressure, limiting practicality. The quest for a room temperature, ambient pressure superconductor continues, a material that could revolutionize power transmission, computing, and countless technologies. Metals at the edge of cold reveal quantum secrets, holding the potential to transform our electric world. Liquid metals beyond mercury exist. Mercury's status as the only liquid metal at room temperature was mentioned earlier, but other metals can exist as liquids at slightly elevated temperatures. Gallium, as we discussed, melts just below body temperature, but several elements and alloys form liquids at relatively low temperatures. Cesium melts at about 28 degrees, though its reactivity makes liquid cesium impractical and dangerous. Rubidium melts at 39 degrees. Francium would presumably be liquid around room temperature if enough could be gathered, but its radioactivity and scarcity prevent any such experiment. Certain alloys combine metals to create liquids at room temperature or below. Gallium, an alloy of gallium, indium, and tin, remains liquid down to about -19 degrees. It's used as a non-toxic alternative to mercury in thermometers and some scientific applications. Fields metal, an alloy of bismuth, indium, and tin, melts at 62 degrees and is used in safety devices like fire sprinklers. Woods metal, containing bismuth, lead, tin, and cadmium, melts around 70 degrees and was historically used for making molds and in metallurgy. These low-melting alloys, sometimes called fusible alloys, have unique applications. They can serve as coolants in experimental setups, as heat-sensitive triggers, or as temporary supports in metal casting that can be melted away after use. Liquid metal research extends to more exotic concepts. Liquid metal batteries, using molten metals as electrodes, are being developed for grid-scale energy storage. The high conductivity and fluidity of liquid metals enable designs impossible with solid electrodes. The boundary between solid and liquid in metals is more fluid than we might expect, with temperature, pressure, and composition determining the state. Metals can be transparent when made thin enough. We think of metals as opaque, reflecting light rather than transmitting it. But at nanoscale thicknesses, metals can become transparent. Thin films of gold, silver, or other metals, just a few nanometers thick, allow light to pass through while still conducting electricity. This property is used in touchscreens, smart windows, and solar cells. The transparent conducting layer on smartphone screens, often indium tin oxide mentioned earlier, could potentially be replaced with ultra-thin metal films in some applications. The transparency of thin metal films seems paradoxical. Metals are opaque because free electrons absorb photons. But when metal layers are thin enough, typically less than 10 nanometers, their optical properties change. Some light passes through rather than being absorbed or reflected. The exact transparency depends on the metal, the thickness, and the wavelength of light. Gold films transmit more light at longer wavelengths, appearing greenish-blue in transmitted light. Silver transmits across a broader range. These metal films are used in low emissivity windows, which reflect infrared heat while allowing visible light through. This improves building energy efficiency. They're used in some thin film solar cells and as transparent electrodes in organic LEDs. Research into two-dimensional metals, materials just one atom thick, explores even more extreme thinness. Metallic nanosheets could combine conductivity with transparency and flexibility, enabling new electronic devices. The idea of seeing through metal challenges our intuitions, but at the nanoscale, materials behave differently. Properties we consider fundamental, like opacity, can vanish or transform, revealing that what a material is depends on scale and structure as much as composition. Metal foams combine strength with lightness. Take a metal, fill it with bubbles, and you have a metal foam. These materials, also called cellular metals, consist of metal structures with gas-filled pores. They can be surprisingly light, sometimes lighter than water, while maintaining significant strength and stiffness. Aluminum foam is the most common, but foams can be made from various metals and alloys. Metal foams are created by different methods. One involves mixing gas-producing particles into molten metal. As the mixture solidifies, trapped gas creates bubbles. Another method uses hollow ceramic spheres embedded in metal. Yet another starts with a polymer foam template coated with metal, then removes the polymer, leaving a hollow metal skeleton. The resulting materials have unique properties. They're excellent at absorbing impact energy, crushing progressively rather than failing catastrophically. This makes them ideal for vehicle crumple zones and protective packaging. They dampen vibrations and sound effectively. Their high surface area relative to weight is useful for heat exchangers. Metal foams are also used in lightweight structures, providing stiffness without excessive weight. Some medical implants use titanium foam, as bone can grow into the porous structure, integrating the implant with natural bone. The porosity can be tuned from less than 50% up to 98% air, allowing customization for specific applications. Metal foams represent a different approach to materials design. Instead of treating materials as uniform solids, engineers create internal structures that optimize properties. The result is materials that seem to defy expectations, metals that float, cushion, and breathe. Metals can be amorphous without crystalline order. Nearly all metals are crystalline, their atoms arranged in orderly repeating patterns, but under certain conditions, metals can solidify into amorphous structures, lacking long-range atomic order. These are called metallic glasses, or amorphous metals. Creating amorphous metals requires cooling molten metal so rapidly that atoms don't have time to organize into crystals. Cooling rates of millions of degrees per second were initially needed, producing only thin ribbons or tiny samples. More recently, bulk metallic glasses have been developed that can form larger pieces at slower cooling rates. These materials, typically complex alloys, resist crystallization better. Amorphous metals have interesting properties. Without grain boundaries and dislocations, the defects that weaken crystalline metals, metallic glasses can be extremely strong. They also have high hardness and excellent corrosion resistance. Some are more elastic than crystalline metals, able to flex more before permanently deforming. However, they can be brittle, fracturing suddenly under stress rather than bending. Applications include sporting goods like golf club heads and tennis rackets, where the material's strength and elasticity provide performance advantages. Metallic glasses are used in some electronic casings, leveraging their strength and ability to be cast into complex shapes. They're being explored for medical implants, precision gears, and protective coatings. The challenge with metallic glasses is manufacturing. Producing large, defect-free pieces remains difficult and expensive. But research continues, seeking compositions and processes that make these materials more practical. Amorphous metals remind us that order is not necessary for solidity. Atoms frozen in disarray can create materials with properties unattainable in crystals, expanding the possibilities of what metal can be. Pure metals are softer than alloys. If you were to handle pure gold, you might be surprised by its softness. Pure gold, called 24 karat, is soft enough to be scratched with a fingernail. Pure copper is similarly malleable, easily bent. This softness limits the usefulness of pure metals for many applications. The reason for this softness lies in crystal structure. In a pure metal, all atoms are identical and fit together uniformly. When stress is applied, planes of atoms can slide past each other relatively easily, causing the metal to deform. This makes pure metals ductile but weak. Alloying introduces atoms of different sizes into the structure. These foreign atoms create obstacles that prevent atomic planes from sliding smoothly. Imagine trying to slide books across a table where someone has placed random objects in the way. The irregularities increase strength and hardness. This effect, called solid solution strengthening, is one reason alloys are stronger than pure metals. Other strengthening mechanisms in alloys include forming small particles of secondary phases that block dislocation movement, or creating grain boundaries that impede deformation. The trade-off is that increased strength often reduces ductility. Very hard alloys can be brittle. Metallurgists balance these properties, creating materials with the right combination of strength, hardness, ductility, and toughness for each application. The softness of pure metals is why gold jewelry is typically 18 karat or 14 karat, mixed with copper, silver, or other metals for durability. Sterling silver contains 7.5% copper. Even platinum jewelry often includes small amounts of other metals. The metals we use daily are rarely pure, improved through mixing, stronger together than alone. Work hardening makes metals stronger through deformation. You might think that deforming a metal weakens it, and in some ways that's true. But there's a paradox. Cold working a metal, deforming it at temperatures below its recrystallization temperature, actually makes it stronger and harder. This is called work hardening or strain hardening. When you bend or hammer a metal, you're creating defects in its crystal structure called dislocations. These are places where the regular atomic pattern is disrupted. As deformation continues, the density of dislocations increases. These defects interfere with each other, making further deformation more difficult. The metal becomes harder to bend, requiring more force. Blacksmiths have known this for centuries. Hammering a sword blade not only shapes it but hardens it. The repeated impacts create a tougher material. Modern manufacturing uses work hardening intentionally. Cold rolling metal sheets makes them stronger. Drawing wire through progressively smaller dies work hardens it, increasing tensile strength. However, work hardening has limits. Excessive deformation can make metal so hard it becomes brittle and prone to cracking. Moreover, the metal accumulates internal stresses. To relieve these stresses and restore ductility, metals can be annealed, heated, to allow atoms to reorganize into less stressed configurations. This softens the metal, allowing further shaping if needed. The cycle of deformation and annealing can be repeated, allowing complex shapes to be formed. Work hardening connects to the fundamental nature of crystal defects. Controlling these defects through mechanical processing, heat treatment, and alloying allows us to tailor metal properties. The interplay between strength and ductility, between deformation and recovery, gives us the materials that build our world. Some metals can heal their own cracks. The idea of self-healing materials sounds like science fiction, but researchers have developed metals with limited self-repair capabilities. These materials can heal small cracks and damage, extending their lifespan and improving safety. One approach uses embedded healing agents. Microcapsules, or hollow channels within the metal, contain liquid metal or other healing compounds. When a crack forms, it ruptures these capsules, releasing the healing agent into the crack. The agent flows into the damage, solidifies, and restores continuity. This is similar to how human skin bleeds and clots to seal wounds. Another approach relies on atomic diffusion. At elevated temperatures, atoms can move and rearrange. If a crack forms, heating the material allows atoms to migrate into the crack, gradually closing it. This requires elevated temperatures and time, limiting practicality for many applications. Some advanced alloys undergo phase transformations when stressed. The stress of a forming crack triggers a transformation that creates compressive stresses, arresting crack growth. This isn't true healing but can prevent catastrophic failure. True self-healing metals remain largely experimental. The mechanisms are complex. Healing is often incomplete, and only small-scale damage can be addressed. But the potential is tantalizing. Imagine aircraft structures that repair minor cracks automatically, or bridges that heal stress fractures before they become dangerous. Research continues, inspired by biological systems that routinely repair damage. Nature's self-healing materials, from skin to bone, demonstrate what's possible. Achieving similar capabilities in metals requires understanding and controlling processes at atomic scales. Each advance brings us closer to materials that don't just endure, but actively maintain themselves, adapting to damage rather than succumbing to it. The universe produces new metals in stellar explosions. The metals around us, the iron in our blood, the calcium in our bones, the gold in jewelry, did not exist at the universe's beginning. The Big Bang created hydrogen, helium, and traces of lithium, but no heavier elements. Everything else was forged in stars. Main sequence stars, like our Sun, fuse hydrogen into helium in their cores. Larger stars, once they exhaust hydrogen, begin fusing helium into carbon and oxygen. More massive stars continue this process, fusing progressively heavier elements: neon, magnesium, silicon, sulfur, and finally iron. But fusion beyond iron doesn't release energy. It consumes it. This halts the process. For elements heavier than iron to form, extreme conditions are needed. When massive stars exhaust their fuel, they collapse catastrophically, then rebound in supernova explosions. The energies involved are so immense that heavy elements are created through rapid neutron capture, a process called the allure process. Neutrons bombard existing nuclei, creating heavier and heavier elements in seconds. Similarly, when neutron stars collide, the merger creates conditions where heavy elements like gold, platinum, and uranium form. Observations of neutron star collisions have confirmed these events as the primary source of the heaviest elements. The metals in your hands were literally created in stellar cataclysms, scattered across space, eventually coalescing into new stars, planets, and ultimately, us. We are, as Carl Sagan said, star stuff, made of elements forged in the hearts of ancient stars. Every metal has a cosmic origin story, a journey from nuclear furnace to Earth, from stardust to civilization. Conclusion: the quiet beauty of metals. And so, dear listener, our journey through the world of metals comes to a gentle close. From the gold that captivated ancient civilizations to the lithium powering modern devices, from the iron supporting our structures to the rare earths enabling our technologies, we have explored elements that shape our world in countless ways. We have seen metals that melt in your hand and those that withstand temperatures hotter than lava, metals that burst into flame and those that resist all corrosion, metals from deep within Earth and those forged in the hearts of dying stars. Metals are everywhere, in the wires carrying electricity through our homes, in the vehicles transporting us, in the buildings sheltering us, even within our own bodies where they enable the chemistry of life. They conduct, they strengthen, they protect, and they connect. Some are beautiful, prized for their luster and rarity. Others work invisibly, essential but unseen. Together, they form the material foundation of civilization. The story of metals is also humanity's story. Our ages have been named for them: Bronze Age, Iron Age, marking the transformations they enabled. Our technologies depend on them, from ancient tools to modern electronics. Our future will be shaped by them as we develop new alloys, discover new applications, and perhaps even mine metals from asteroids beyond Earth. As you lie here, letting your breath slow and your mind settle, consider the metals around you, the device you may have used today, the building protecting you, the utensils you ate with. All owe their existence to these remarkable elements. Metals bridge the microscopic world of atoms and the everyday world we inhabit. They connect ancient stars to modern cities, deep earth to high technology, practical necessity to aesthetic beauty. Each metal, from the most common to the rarest, has its own character, its own properties, its own history. Some we have known for millennia, others we discovered only recently. Some we mine from deep underground, others we create in laboratories. But all share the essential nature of metals, that unique combination of properties that makes them so useful, so versatile, so central to our lives. The atoms within metals, arranged in their crystalline patterns, vibrating with thermal energy, sharing electrons in their metallic bonds, create the strength and conductivity we depend on. At room temperature, most metals sit solid and still, their atoms locked in place yet ready to conduct heat and electricity, ready to be shaped and formed, ready to serve. And now, as our exploration draws to a close, let the quiet presence of these elements bring you peace. Imagine the copper in your walls, silently carrying electrical signals. Picture the steel beams in buildings, patiently bearing loads. Envision the aluminum in aircraft, light but strong, carrying passengers across continents. Think of the calcium in your bones, giving you structure and support with every breath you take. The world of metals is both vast and intimate, both ancient and ever new. From the gold mask of Tutankhamun gleaming through millennia to the latest titanium alloy in a spacecraft, metals endure and adapt. They are transformed by fire, shaped by pressure, combined in countless ways, yet remain fundamentally themselves, elements from the periodic table, each with its own atomic identity. As you drift towards sleep, let go of the details and simply rest in the knowledge that metals are all around, supporting and enabling, working quietly and reliably. They ask nothing. They simply are, performing their functions through the laws of chemistry and physics. There is something deeply calming in this reliability, in the predictable properties of elements, in the way copper always conducts, gold always resists tarnish, iron always strengthens when alloyed with carbon. The metals we have explored tonight will still be here tomorrow and the next day, and for centuries to come. They weather and age, they corrode and transform, but they endure. The same elements that formed in stars billions of years ago cycle through our civilization, used and reused, melted and reformed, serving generation after generation. Let this continuity bring you comfort. The metals that built ancient Rome and modern cities, that armed warriors and healed patients, that decorated kings and empower everyone, they persist. In their persistence, they offer a kind of permanence in an ever-changing world. Close your eyes now and breathe deeply. Feel the stillness settling over you like a soft blanket. Imagine you are surrounded by a world of metal, strong and protective, conducting and connecting, holding everything together. The framework of civilization, the foundation of technology, the scaffold of progress, all made of metals that were once stardust, once part of ancient stars, now part of Earth, now part of our lives. Each breath you take brings in oxygen that will bind with iron in your blood. Each heartbeat pumps calcium through your body. Every thought requires sodium and potassium flowing across nerve cells. You are not separate from metals, but part of the same story, built from the same elements, connected through chemistry and physics to the universe itself. Rest now in this connection. Let the knowledge of metals, their properties and purposes, their histories and futures, fade into the background. What remains is simply the quiet presence of matter itself, arranged in ways both beautiful and useful, waiting patiently through the night. Metals do not sleep, do not dream, do not rest. They simply exist, atoms bonded together, electrons flowing freely, ready to serve when called upon. There is peace in this constancy, in the reliable nature of elements. As you surrender to sleep, you join a different kind of constancy, the rhythm of rest and waking, the cycle of consciousness and dreams. The metals will be here when you wake, unchanged, steadfast, ready for another day of bearing weight, conducting current, forming structures, enabling life. They will continue their ancient work, connecting past to future, supporting the present, making possible all that we do. Drift now into that peaceful place where thoughts dissolve and awareness fades. Let the story of metals become a distant memory, a collection of facts and figures that held your attention but now release you to sleep. The journey has been long and full of wonders, but every journey must end, at least for now. Breathe in deeply, breathe out slowly. Feel your body heavy and relaxed, supported by materials that include metals processed and shaped, by beds with steel springs or aluminum frames, in rooms with copper wiring and steel reinforcements. You are held by the work of metals, as humanity has been held for thousands of years. And so we close this chapter, this exploration of elements that glitter and conduct, that strengthen and resist, that enable and endure. May the quiet constancy of metals bring you to a place of deep rest and peaceful dreams. If your eyes are still open, You may now close them. If your mind is still active, you may now let it settle. The metals of the world will keep their vigil while you sleep, working silently, reliably, eternally. Good night, rest well, and let the metallic world around you hold you safely until morning comes. Sleep now.